prices fall off, right? And employment and the unemployment rate are likely to rise. And that is the cost, okay, of reducing inflationary pressure in the economy. Looking here, this is the graph of the federal funds rate. We had this on Tuesday as well, and notice something. Typically, the federal funds rate rises sharply before recessions. Okay, that's not the only time it rises. It rose sharply here, here, and here, but it didn't cause a recession. But before every recession, here, 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 and so on, the Fed funds rate rises sharply. And of course, now it's going up again. Okay, here. All right. Notice also, okay, the flip side of that is also true, that typically in an expansion, recall the expansions are here. On the expansions, at the beginning of the expansions, at least, interest rates typically fall. Okay. And lastly, looking at inflation, inflation typically falls in recessions. We have a name for that. When inflation falls, we call that disinflation. Okay. So I want to use a symbol. I introduced it last time, but I want to use this, introduce a symbol here. Inflation is equal to the percentage change in some price index, possibly the consumer price index. There are other price indices as well, such as the personal consumption expenditure index, is the wholesale price index. There's the GDP deflator. But typically, inflation receives a headline in the newspapers when the percentage change in the consumer price index is positive. We want a symbol for this. Okay, we're going to use the symbol pi for inflation. Now, we're not saying that inflation is always 3.14159. We're just reminding ourselves that this is a whole lot to write out. And so we'll just use the symbol pi for inflation. All right, the percentage change in inflation. So for instance, so when pi is positive, which is this entire region of this graph, here's the zero, here's where pi is positive, those are inflationary periods. Okay? There's also a zone down here where pi is negative, we're below the zero. This is called deflation. That's an E. Okay, negative inflation. You can see, going back to the 1950s, there's been 1, 2, 3, 4 deflations. Okay, and we got kind of close in COVID, but not quite there. Okay, but what we're talking about here is a reduction in inflation, right? Typically, inflation falls. When inflation itself falls, that's called a disinflation. And you can see a variety of disinflations on this graph. Here's a disinflation. In 1980, inflation up nearly 15%, and it came down. That's a disinflation. Here's a disinflation, okay? Of course, if you have enough disinflation, you may get to a deflation, okay? And that happened in the global financial crisis. Here's another disinflation here. Here's another disinflation here, okay? And what Jerome Powell is promising, okay, by that statement, they strongly committed to reducing inflation, is they're strongly committed to disinflating the economy and bringing this thing back in this direction. Okay? But as he mentions, the cost of that is a slower economic activity, a lower economic activity, and a lower employment. That is a rise in the unemployment rate. Somebody will have to pay for it. Right? Those people who don't get jobs that they would have ordinarily received, right? Those people will be paying for the disinflation. We'll talk about this later in the courts. But this is happening right now. Some other statements by the Fed. The Fed chair also said that recent indicators of spending and production have softened. Okay, notice what he says here is they've softened, they haven't fallen. Okay, indicators of spending, okay, are wholesale and retail spending. And if you look at wholesale and retail spending, say from 2020 to 2022, June, they're doing something like this. They're starting to slow, but not falling yet. Okay, that's what we mean by softening, right? The slope has fallen off, but has not yet declined. Okay, production, of course, is real GDP, but it also is industrial production. Industrial production is also rising at a slower rate right now. Okay, so it's increasing, but at a slower, ever slower rate. Okay, and of course that's what happens when you're near a peak and then a turnaround falling off. Okay, so notice this statement is referring to two elements of what we call the NBER definition of a recession. Okay, wholesale and retail spending, real GDP, and industrial production. Okay. Next, he also says, however, that job gains have been strong in recent months. Okay, that means the unemployment rate has been low and falling and stable, and employment has been rising. That indicates a strong economy, right? And at the moment, the last reading we have from June is that the number of job openings still exceed the number of people looking for jobs. Okay, that's good for people looking for jobs. There's more than a one-to-one relationship between job openings and job seekers. Okay, so that indicates a robust and strong labor market. So that would indicate economic strength as opposed to economic weakness. Okay, he said as of yesterday, we're not in recession now. Okay, but real GDP fell in Q1 and is likely to be stagnant in Q2. Well, we know from this morning, another piece of economic data from this morning, we learned that in Q2, real GDP fell by, I think it was 0.7%. Okay, which is small, right, at an annual rate, but it's not nothing. It fell, right? That's not a good signal. And he reminded people in the press conference of exactly what we talked about on Tuesday, that a recession, and this is practically the definition of the NBER. I'm very surprised he had it right in front of his brain so he could say it. A recession is a broad-based decline in many industries sustained for more than a couple of months. Okay, he reiterated that particular definition for the press. Okay, and he followed up with saying that it does not seem to hold now as the labor market is strong. Okay, and I would add to just help him out. I would add also that spending at the wholesale and retail level is also relatively strong. Okay, so there's if you will, a mixed signal here of the strength of the economy at the moment. Okay, retail and wholesale spending is still strong, although they've softened a bit. Job gains are strong. Okay, but real GDP has now declined for the second consecutive quarter. Incomes are probably still growing a little bit. Industrial production is still growing, but at a slower rate. All right. What I want to take away from this is to think about our two common definitions of recession. Okay, the first definition is what you very often hear in the press, that recession is equal to 2 consecutive quarters of falling real GDP. So in terms of our notation, falling real GDP would mean the growth rate of GDP. Remember, we used a small g sub x would be the growth rate of x. So if we wanted to talk about the growth rate of real GDP, we'd have small g with a subscript of real GDP. 2 consecutive quarters of real GDP falling would be the growth rate of GDP was negative for 6 months. Okay, well, we've kind of achieved that as of this morning's data release of real GDP in the second quarter of 2022. But we also have the NBER definition of a recession, which recall is a significant decline in economic activity spread across the entire economy, okay, affecting more than just one industry, but many industries, lasting for more than a few months, and typically evident in all of these five variables. And the five variables are real GDP, our variable Y, real income, okay, real income, employment, industrial production, and wholesale and retail sales. And of these, we know that this has fallen. This we don't know about, but it's likely to be rising. Employment is still rising. Industrial production is still rising, and retail and wholesale sales are still rising, although all of these here have softened. Okay, the first one has certainly declined. All right, so this is a mixed signal. If we're using the 2 consecutive quarters definition, then the U.S. economy would be in recession. Okay, if we use the NBER definition, the U.S. economy would not yet be in recession, right? Because though GDP fell, these other indicators are softening, but they're not yet falling. Okay, and there's a little bit of a conflict, but it is very clear from Jerome Powell's statements that the Federal Reserve, central bank of the country, will continue increasing the target range for the federal fund rate, which will continue to increase borrowing costs for business and banks, businesses and households, which will continue to constrain spending and demand, right? And that will eventually push the economy into recession. And he's very clear and open about that. When somebody tells you what they're going to do, you should believe them, particularly the Federal Reserve. Okay, and that was news. That was headline news in all of the newspapers and websites this morning, and it is exactly what we talked about on Tuesday. Okay. Having said all of that, and it's a topic of the last third of our course. Having said all of that, I want to remind you, okay, of our topic right now, of economic growth. And recall that economic growth will overwhelm any recession that's coming. That here's the Great Depression in the 1930s. Unemployment rate of 25%. The unemployment rate in the United States will not even reach 10% in any coming recession. Here's the global financial crisis. The unemployment rate reached 10% there. Right, but economic growth swamps all of those. Okay, these are each one, as I mentioned, 1/2 a grid line, whereas economic growth on this chart is 10 grid lines. Economic growth swamps everything. Okay, that's the most important thing, and that's what we're turning our attention to in this first part of the course. Okay, so. Recall the daunting task that was laid out by Kaldor and his research team. The daunting task was to build a model that yields all of the Kaldor great ratios, all of these 6 or 7 ratios. As an economic model, or as a professional research economist looking at this, my head kind of explodes, right? To think, I have to write something down that does all of this? How's that possible? Well, if you're a genius like Robert Solow, okay, apparently it's relatively easy, okay? Solow stepped up, he looked at the Kaldor ratios, and he said, I can do that. And that's the model we're turning our attention to today in the next couple of days. Recall, Solow builds the aggregate production function, where real GDP, Y, is made up of capital and labor. Okay, produced by capital and labor, and has some properties. The properties are constant returns to scale, okay, and diminishing marginal productivity of both labor and capital. Okay, alrighty. Let's take a look at these. Right, recall what constant returns to scale means. Constant returns to scale means if all inputs change by a proportion lambda, then output changes by that same proportion lambda. Okay, and what we mentioned the very end of last time is that constant returns to scale is a very general assumption. Okay, it means that size doesn't matter for economic growth. That small countries can grow fast or small countries can grow fast or slow, and big countries can grow fast or small or slow. If you pick one of the other returns to scale, increasing returns to scale, for instance, then only large countries can grow fast, and you've kind of biased your model, right, to get that result right away, right out of the blocks as soon as you start. Likewise, if you have decreasing returns to scale, only small countries can grow fast. But then, of course, they get big, right, since they're growing fast, and then they slow down and stop. And that doesn't make any sense either. Okay? Constant returns to scale is right in the middle. Okay? And it says size doesn't matter for economic growth. Small countries can be fast growers. Big countries can be fast growers or slow growers for that matter. Okay, and it turns out Robert Hall in the 1980s, 30 years after Solow, demonstrated that most U.S. Industries operate in constant returns to scale because they have constant average total costs and constant marginal costs. That's one of the properties of constant returns to scale. Okay. The other property of the aggregate production function, this y equals f of k and l function that Solow uses, was diminishing marginal productivity of capital and labor. And what that means, right, is the marginal productivity themselves, the MPK, this is the marginal product of capital, the MPK, okay, is the partial derivative of the production function, partial derivative of y, or partial derivative of f with respect to k. And it tells you the output produced by one extra unit of capital or an incremental unit of capital, keeping labor fixed. That's what a partial derivative does. L is fixed. And the idea on this would be, well, if you bring an extra piece of machinery, an extra piece of capital into the factory, into F, keeping labor fixed, how much extra output do you get? Right, one unit comes in here, and how much extra do you get here? That's a partial derivative, right? And it's the marginal product of capital, right? The marginal product of labor, the MPL, okay, is the partial of the function with respect to L. And it says if you keep capital fixed and increase this by 1 unit, how much extra output do you get? Okay, and that's the partial derivative here. So if you have the same factory, same pieces of machinery and equipment, everything else the same, but you hire one extra worker that day, how much extra output does that factory produce in that particular day? That could be associated with that extra one worker, and that would be the marginal productivity of that worker. Diminishing marginal productivity of capital means the second derivative is negative. The derivative of the marginal product of capital is negative. Okay, the derivative of the derivative is the second derivative, and this is the condition for diminishing marginal productivity of capital. Okay, and the idea here is the following: as you add a given factory, a given number of labor, as you add more and more machines to that factory starts getting crowded with machinery. Okay, the factory floor gets crowded. Workers have too many machines to work with. There's only so many machines I can work with. Right now, I'm working with a laptop here and my iPad Pro here. That's enough. I couldn't work with another piece of machinery. It wouldn't be possible. It would reduce my productivity. I'd have to deal with it over on the side here. Okay. As more machines come into any production site, holding everything else fixed, the number of workers fixed particularly, the productivity of those new machines has to be smaller due to crowding. And that requires the second derivative of the production function or the derivative of the marginal product with respect to capital to be falling, okay, negative. Right. Likewise, for diminishing marginal product of labor, the second derivative of the production function with respect to L or the derivative of the MPL with respect to L is negative. Okay. That's the idea. So again, if you think of it this way, you have a fixed factory, a fixed number of machines, and more workers are being added. Okay, the machinery is being crowded by workers. More and more workers are trying to work on that fixed number of machines, and by crowding one another, they reduce one another's productivity, their marginal productivity. Not through any fault of their own, it's just getting crowded there. And that's diminishing marginal product of labor. All righty, so to take a look at this, let's take a look at the production function that Solow assumes. We mentioned last time that I think we mentioned last time that Solow assumes what's called the Cobb-Douglas production function. I think there's one S in Douglas. In any case, it has this particular form, a particular functional form, that y is equal to some function of k and l, and it's this function of k and l. K is raised to the alpha power, and L is raised to the 1 minus alpha power. This function has constant returns to scale. We showed that last time. Okay, and alpha is in the open interval 0, 1. This expression here means that alpha is strictly between 0 and 1. Okay, not 1, not 0, all right, but somewhere in between. It's a fraction, like a half or a quarter, a third, something like that. Okay. Solow uses this aggregate production function in his examples from his famous paper, and we will use this production function as well. Okay. Notice the capital and labor are multiplied together in this Cobb-Douglas production function, which means if one of them is 0, okay, if capital is 0 or labor is 0, you can't make output. Okay. And that should make sense. In a modern society, you definitely need some capital to make output, and you also need some labor to make output. Even if it's just an automated factory, you just come in and turn on the lights. Okay, turn on the electricity. To check for diminishing marginal product of labor and capital, we want to first find the partial derivatives. The marginal product of capital is the partial derivative of this function. And if I've done this right, you should check me here. Always check my math mentally. Okay, this is the partial derivative. We use the product rule here. I'm sorry, the power function rule. So k to the alpha times L to the 1 minus alpha. The derivative there, the partial derivative, is alpha times k to the alpha minus 1 times L to the 1 minus alpha. We just differentiate on the k. Okay, and then to check the second derivative, that if the second derivative is 0, we take the derivative of the first derivative. And that second derivative, I'm differentiating now on this with respect to k. That's what this says. Okay. The 1 minus alpha minus 1 power comes down. It's alpha minus 1 times alpha times k to the alpha minus 2, L to the 1 minus alpha. And that's negative because alpha is between 0 and 1, because this thing becomes negative. Okay, that first term is negative. And so we have diminishing marginal product of capital. We can do the same thing for labor. I'll just put the sign up here. Here's the derivatives. And in fact, we do get a negative sign there. You should check this on your own. In the privacy of your own home later tonight, or on the recitation problem set, make sure you can show that this is the second derivative of the production function with respect to L. The partial derivative with respect to L is negative. Alrighty. So this function satisfies the second criteria that Solow has: constant returns to scale and diminishing marginal productivity of both factors, because we think that's normal. Okay. Take the diminishing marginal product of labor. Suppose I'm the one worker here at the moment. I'm the labor. Okay. If I had a second professor here also teaching, right next to me talking here, would that be very productive? No. We would be getting in one another's way. The first one, you absolutely need me here to teach this course, right? I'm very, very productive, I hope. The second one would have diminishing marginal productivity. They would be much less productive than I am, right? Not because of who they are, simply because of the crowding on the screen and our voices crowding one another. Okay, that's the concept of diminishing marginal productivity of labor. They would be crowding the production process, my Zoom screen here, with another professor. All right. So clearly, in these last two examples, alpha plays a crucial role here. Alpha here and alpha here. It gives us the sign here. Okay, what exactly is alpha? Okay, alpha is the capital share of GDP. Okay, and what we mean, it's between 0 and 1. It's a fraction. Okay, alpha represents the total payments to capital as a proportion of real GDP Y. Okay, so we can think of alpha in the following way: all the payments to capital, okay, as a fraction of GDP in the denominator. I recall GDP is our variable Y, or it should be real GDP is our variable Y. And what are the payments to capital? Okay? The payments to capital are things that capitalists earn. Okay? Payments to capital will include profits that businesses earn, rents, because the landlord owns land, okay, and they collect rent. The ownership of funds allows you to earn interest. Okay, payments to capital are payments from due to ownership of some factors of production, land, capital, or financial funds. Okay. It turns out in the United States, the capital share of GDP is about 30%. Okay, alpha that is about 30%. Capital gets paid about 30% of overall national production, 0.30. Okay, and if we had the production function here, k to the alpha, L to the 1 minus alpha, Cobb-Douglas production function, we'd have a 0.30 in the numerator for k. I'm sorry, in the exponent for k. And that must mean, if this is the function, that L must have an exponent of 0.70. And that's in fact also the case. That implies the labor share of GDP, which is 1 minus alpha, right? The exponent, 1 minus alpha, is 70% or 0.70. And of course, the labor share, this 1 minus alpha term, the total payments to labor as a proportion of GDP. And that would be in the numerator, and here's real GDP in the denominator, the numerator, and Y. And these include, of course, what workers get paid. They get paid wages, they get paid fringe benefits, vacation days, sick days, time off, personal days, eyeglass care, medical insurance, I should say, maternity leave, paternity leave, elder care leave, transfers from the government. All of those things are things that workers earn, labor earns, and they all contribute to the total payments to labor in the numerator, and then we divide that by real GDP, and that get the labor share. Notice also that labor gets the bigger share. This is the capital share. Right? Labor gets more than twice the share of GDP as capital gets. Okay, capital only gets 30%, and labor gets the overwhelming majority. I think most people find that surprising. Here's a graph of, this is from your textbook, a graph of the labor share in the United States. And here's 60% and 70% of 0.7. This is 60 and 80% rather. This is 0.70 right in there. And it's roughly constant. It's fallen off a little bit since about 2001 or so. It's fallen off a little bit off of this line, but we're going to keep this. This is 1 minus alpha. We're going to keep this as a parameter here. It hasn't fallen off very much. And considering how complicated this variable is, it's all of the workers in the United States. Okay, there are about 160 million workers in the United States, each of them getting paid a different wage. Okay, different benefits, different transfers, different eyeglass care, healthcare, and so on. As a fraction of real GDP is around $20 trillion. And somehow that number always comes out to be 0.70. It's kind of a miracle. And we'll call this kind of a structural parameter of the US economy and most other countries' economies, that the labor, it doesn't have to be 70%. But the labor share and the capital share are relatively fixed, which is an astonishing empirical observation. Right? They're complicated variables, and yet they tend to be roughly constant. Okay. So next, building the model. Here's the Solow model. This is the Cobb-Douglas production function. It has constant returns to scale, and it has diminishing marginal product of capital and diminishing marginal product of labor. And now we're going to build out the entire rest of this model. Okay. So hold on to your hats. I think this warrants a period. Okay then. So first, and this is the kind of a key step in the Solow model. What Solow does straight away is transform all of the variables into per worker terms. Well, workers are L, okay, and per means dividing. So what he's going to do is, in this entire model, it's not something you would do, but recall Robert Solow is a genius, right? He's kind of the, I don't know, the Mozart of well, LeBron James of well, Michael Jordan of economic growth. Um, he's going to do this to all terms, and that's going to be like a little trick that we'll work through on in every single variable that we introduce. We'll then divide it by L. Introduce a variable, divide it by L, and so on. Okay, so what that means straight away, we only have the one variable, this function y. We're going to divide that by L. And when we do that, okay, we have, of course, y over L on the left-hand side and this entire expression over L on the right-hand side. And then we can do some simplification. Right? Recall the rules of exponents. Okay, this is a L to the 1 in the denominator. We have an L to the 1 in the numerator. Those two cancel. When you have a variable in the other part of the fraction, that exponent is takes on a negative sign, and then when you have the same base, you add exponents until we get k to the alpha. When we do this cancellation here, not with the alpha, and here, we get k to the alpha L to the minus alpha. And then one of the other rules of exponents, the minus sign in an exponent means that the variable belongs in the other part of the fraction. And so that means I get this expression. Right? That L to the minus alpha means L is downstairs to the alpha power. But now looking at this, right, you see what's going to happen next? What's the next step? Someone answer me. This is my first question for the class. What's the next step here? Answer me in chat. Okay. No? Someone? What do I do next? Look at that last expression. Can you make that simpler? That's right. Arya. There's a common power. So what would the, that's right, Arisha, Arshita, sorry. So what would the answer be here? What's the next line here? You can type it out. That's right. Almost, Ellie. Yeah, almost. I'm going to kind of, this is not the right terminology. I'm going to factor out the A, the alpha to this, right? Isn't that, there you go. That's what you wanted, Ellie. Eli, sorry. You want this. It's K over L, right, to the alpha power, okay? Now notice what we have at the beginning. We have Y over L, and now we have K over L to the alpha power, okay? What he does is, again, something you probably would not do. Okay? He's going to redefine variables here. Okay? That's what we have so far. And he's going to say, first, let's interpret this. It says this is output in the numerator, or real GDP, and it's a labor in the denominator, or workers. It says that output per worker or output per labor depends upon capital per worker over here, K over L. Does that make sense to you? The amount of output an average worker can make will depend upon how much capital the average worker has to work with. That should make sense. Recall, there's no technology here. Right? So there's nothing else to help the worker out. So if the worker has more capital on average, the average capital, they'll be able to make more output. Okay, to this alpha power. Right? So he's now going to redefine variables. He's going to redefine Y over L as small y. That's what these three bars mean, right? Here, 1, 2. That's a definition. And these three bars here mean small k is equal to K over L. And when he does that, since this is now small y, and inside of here is small k, we get the following expression. Small y, right? This is small y, is equal to small k, and of course there's an alpha. That's a much neater and concise form of the production function, and it's in terms of each worker, per worker terms. There's a name for this production function, and it's called the intensive form of the production function. And notice how we get it. We start up here with this form of the production function, and all we did was divide both sides by L. And then we worked out the algebra, and we got this form. That's the form we'll use over and over again. And it always looks like this. When the production function starts out like this, you can be assured the intensive form of the production function looks like this at the bottom all the time. But the terms have to be properly defined. Small y, and you have to have a small y. You have to have a small y in your notation. Here's my capital Y, right? Here's my small y. Here's my capital K. Here's my small k. You have to have that notation. They mean different things. Those of you who are coming from, well, I don't know, physics or mathematics or engineering, this standard where you have a slightly different notation, an uppercase letter and a lowercase, and the lowercase means something different. Here, the lowercase or small letter means in per worker terms, right? And that's the one this is the one we will work with over and over again. So, I am one step away from blowing your minds, just one step, okay? I want to graph this function, okay? Here's the function I want to graph. Somebody in chat, what does this function look like? I want to graph it. I understand that you can download the clean version besides, but describe to me what this function looks like and why. Remember, if we're graphing a function, we need to know a few things about it. We need to know its slope, and we need to know where its intercepts are, where its roots are, right, and where its intercepts are. So maybe that last one is the way to start. Where is this function's intercepts? Yeah, Luke, 0, right? What do you mean by 0, Luke? You mean, describe that. If k is equal to, if small k, I should say. Right? If small k is equal to 0, then output, that's right, then output is equal to 0, right? You everyone see that logic, right? No, I'll write it here. If small k is equal to 0, then small y is equal to 0, okay? That's the origin. Next, that's the mathematics of this function, right? Does that make sense? Someone else, does that make sense? Economic sense, intellectual sense. Someone? Yeah, I'm looking at Luke's, yes, and Luke and Eli, I think it was, mind blown. Okay, not yet. That's not it yet. It's coming. It's really coming. All right. But that's not quite it. Yeah, that's right. Yinan Zhang says the same thing. If workers have no capital to work with, if the average worker has no capital, then they can't make output. They can't make goods and services. If you don't have any, I mean, going back, even in the Stone Age, right? When we were, our species was living in caves and all, you needed a stone to make something. I mean, that stone was a piece of capital, okay? If you don't have any capital, you can't make any goods and services, okay? So the origin makes sense. Does that make sense to you? Okay, I see. Okay, I've motivated too much on that. Okay, so that should make sense. So this function comes whipping out of the origin, comes out of the origin. Okay. Next, what does this function look like? That's a harder question in analytic geometry. Remember, here's the function we're talking about, and alpha is between 0 and 1. So what kind of function is this? It has a name. It's not an exponent. Well, it is kind of an exponential function, but there's another name for this function. Is it possible for alpha, given these conditions, is it possible? Yeah, that's true too, but not quite what I'm looking for. It's not a guessing game. Let's take a number inside here. Alpha has to be between 0 and 1. Suppose alpha, it's not logarithmic. Suppose alpha is 1/2. Is that allowed? First of all, is it allowed by this condition? Yes. Okay. And so if alpha is 1/2, what kind of function is it? Not asymptotic. It's the square root function, right? If alpha is half, it's the square root function. The half power and half exponent is the square root function, right? And what does the square root function look like? It's upward sloping like this, right? It comes up like this. It doesn't have to be a square root. Alpha could be, alpha could be a third. In the United States, we know alpha is 0.30, which is close to 1/3, but it's a root power. It's a function that starts at the origin and has this root function shape. It looks like this. Please don't have your mind blown yet. It's going to come, I assure you. So here's this function. And of course, it goes all the way down to the origin. For some reason, it's not showing up on my slide thing. But it comes all the way down for the origin. It comes whipping out of the origin, as I mentioned. It comes whipping out of the origin. And goes like that. Okay. And that's the shape of the square root function, a cube root function, and so on. And you're going to think I'm crazy here. Maybe you already think I'm crazy. But you're going to think I'm crazy. I want everybody in the class to take their right hand or their left hand, take their right hand, and do this shape. You see what I'm doing on the slide? Do that. Yeah, you see that? Isn't that fun? Yeah, yeah. That's the shape of this function. Okay, and we're going to have in 30 years from now, we're organizing a reunion of Econ 100B. Already organizing that. And when we have the reunion, if you use this hand signal, you'll get into the reunion for free, okay? This is a very important shape in economics, and it's crucially important shape in this particular model, okay? Has everyone done this in chat? Has everybody done this? Confirm, please. All right. Thank you, Luke. Thank you, Angela. Very good, Vincent. Okay, Elijah. Okay, Penelope. I get it. Okay, that's on. Okay, this shape. You see it? If I had a microphone here, I would just drop it. I do my mic drop. That's it. I've just done everything. Everything else in the model comes from this shape. Okay. And what does this shape say? Okay. It says as you increase capital per worker, notice capital per worker, the small k is on the horizontal axis, and output per worker, the small y is on the vertical axis. As you increase capital, say 1 per worker, 2, 3, 4, 5, so on, you get, if you're starting at the origin, you get a tremendous amount of extra output per worker here. And then the next one, you get a little bit more. And then the next one, you get a little bit more after that. What's going on here? What's this property? Yes, not quite. Luke has not quite the answer. I'm going to go into chat here. Angela has 99.9%. It's diminishing. Look at what she wrote. It's diminishing marginal product of, let's see if I can copy that. I can't copy it. It's not quite diminishing margin. No, she's almost right. It's not diminishing marginal product of capital K. What's the horizontal axis? Yeah, diminishing marginal product of small k, because small k is on the axis. So she was 99.99% right on, but it's diminishing marginal product of small k. And recall, small k is capital per worker. Yeah, good effort there, Angela. That's the key insight. So what does that mean? Let's put that into context of what we know diminishing marginal product is. It says, as you give workers more and more average capital, as the average worker gets more capital, as the average capital stock per worker rises, 1, 2, 3, 4, 5, here, capital per worker. Every worker has 1 unit of capital. Now every worker has 2 units. Every worker has 3 units of capital. Every worker has 4 units, 5 units, and so on, okay? The output that you get from each additional unit gets smaller. You go from 0 to this one, it's tremendous, right? The marginal product of small k is huge there, but then it's only this big on the second step. And it's only this big on the third step, and it gets increasingly small. It gets smaller and smaller. You can see the function is flattening out, right? Someone mentioned it was asymptotic. I don't want to use that terminology, but you can definitely see when we use our famous hand signal, right? Everybody's hand signal. Your hand flattens out. This function flattens out. Okay, that is the mic drop. Okay, that's the mic drop. So this expression shows, this graph now shows you the diminishing marginal product of small k. And that must mean, okay, the derivative of, I'm sorry, not the partial derivative, it's the total derivative, right? The derivative of small y with respect to small k is equal to alpha k to the alpha minus 1. That's positive, but the second derivative, sorry, I keep writing a total partial derivative. The second derivative, which is alpha minus 1 alpha k to the alpha minus 2, that's negative. It's terrible right at the end there. Okay. And that leads to a whole variety of consequences. Let's take a look at them. Okay. Now, some people have called this Solo's big surprise. Okay. I'm one of those people who've called it. Okay. Here's why. Okay. Looking at this function, it has two implications. One implication for rich countries, that's the function here, and one implication for poor countries. And it comes out of just the shape of the function. Okay. So here's the implication for rich countries. Here's the function, right? We know it has this shape. Right? Where are rich countries on this graph? Someone in chat. Yeah. Towards the extreme right-hand side. That's right. Rich countries have to be out here. They have to be at K, call it rich. Well, look at where that means they are. They're out here. They're in the flat part of their function, right? That's where diminishing marginal product of small k is really biting, is really cutting in, okay? And so what then is the implication? There's an implication here. Somebody's got to find it. I can't tell you. You have to find it. Rich countries are way out there at K. How can they increase their output per worker? That's close, Lucas. Lucas is quite close. Okay. Let me read Lucas's statement here. Lucas says, rich countries can't grow very much richer without a lot of effort. I would just change that. If they increase their capital stock, if they move from here, Lucas, right, to here, right, they only move up a little bit, right? If they increase their capital per worker, their average capital per worker, and rich countries have lots of workers, so they've got to increase their capital a lot. That's what he means there. That's what Lucas means there. They won't get very much extra output. So how do they increase output per worker? Yes. Mind blown, Lucas. Mind blown. So since increasing the capital stock per worker cannot increase output per worker, rich countries must depend upon technological change. Rich countries' growth of output per worker, I don't usually write things out, but it's so important. Let's slow down a bit. Depends on technological change. All right, because they've reached the point of strongly diminished marginal product of capital per worker. Rich countries are rich. I'm here in New York City. There's all kinds of buildings. We have a tremendous amount of capital stock. We've built it all out. We went from here way out to there. And adding more capital just won't do it. We've reached strongly diminishing marginal product of capital per worker. And so, rich countries depend upon technological progress and technological change. Boom. In other words, another way of saying that is investment for rich countries. Investment in capital is not what's important. It's technological progress. Notice how he gets at this result. Solow gets at this result because this model doesn't have technology in it. Okay? It's the model without technology. He shows you if you're a rich country and you just do all this, you're going to run into diminishing marginal productivity of capital per worker, and that's going to slow you down. And so you must then depend upon technological change in rich countries. With me? All right. Very good. All right. That's the implication for rich countries. Next slide. The implication for poor countries. Where are poor countries on this graph? Somebody show me. Somebody tell me in chat. They're near the y-axis. They're over here. They're down in here. Call this K poor. Well, look at where they are, right? They're in the steep part of the function, right? They don't have very much capital. Here's the origin. They're poor. They have a low amount of capital per worker. Okay, they're in the steep part of the function that's still rapidly increasing. They have a relatively large 1 unit change in capital, and their output per worker will go from Y1 to Y2, small y2, and that's a relatively big increase. Okay, and so then the implication of this simple graph that has this function, right, has a different implication for poor countries. What should poor countries do to grow their output per worker? They should depend upon investment. Poor countries can depend on investment. What is investment? It's the purchase of new factory machinery and equipment to increase their capital stock and capital stock per worker, and that will lead to fast growth in small y, which is of course y over L. And so the implication for poor countries is completely different because they're in a different part of this function. Okay, it's a policy implication directly from this function. Okay? It's a Cobb-Douglas production function. We know it starts out like this. K to the alpha, L to the 1 minus alpha has constant returns to scale and diminishing marginal product of both inputs. And it ends up in the intensive form like this, which is the one we're graphing here, right? And it has two different implications for rich countries and poor countries. And rich countries and poor countries policymakers should pay attention to this implication. Should pay attention to this graph. It all comes out of the slope of this function, of this hand signal. Okay, with me? But if you're looking at the slides from the clean version of the slides from Canvas, and I uploaded to Canvas earlier this afternoon, there is another implication or another challenge, if you will, right? And that's on the next slide, okay? This graph also has a challenge for middle income countries, okay? Again, I'll ask you, somebody in chat, do me the favor of where are middle income countries, right? That's an easy answer. Not developing country, let's call them middle income countries. Yeah, we referred to them on Tuesday, right? They're right around the world average, right? No, not near the peak. They're middle income countries. Remember, the rich countries were out here. The poor countries were out in here. The middle income countries are in the middle. Yeah, running in the middle. They're in here, right? These are middle income countries. And recall that graph I had, a graph I had of various middle income countries near the world average. There were two of them, right? You remember? You're a little bit ahead of me, Lucas. What were the two middle income countries I highlighted? Do you remember? They were Brazil and China, right around the world average. Yes, right around the world average. So they're in here. I like Brazil. I love Brazil. Um, Wonderful people and culture and country. But let's talk about China. China is right in here, right in the middle income, not a developing country anymore. Okay, but in the middle, right at the world average, maybe just slightly above the world average now. The chart I showed you on Tuesday was from 2016. Okay, so a little bit above the world average, but not that much above the world average. What is the challenge? Looking at this graph and what we know about rich and poor countries and the analysis we did on rich and poor countries on this graph just earlier, what's the challenge for China and all middle income countries like Brazil and others? Do you see what the challenge is? Let me give you a hint. Where were they and where are they going? If they're a middle income country, where were they and where are they going? That'll help you. Tell me in chat. Sort of. Where were they? Middle income countries were all formerly poor. They came from here. Here they are in the middle. And where are they going? They're going out here, right? The rich countries. So, no. Yeah, Dasan. Yeah, Dasan's getting closer. If you're paying attention in chat, Dasan's getting closer. Okay. What was their development strategy? What does this graph imply for their development strategy before? And what does this graph imply for their development strategy going ahead? I'm waiting you out. Before they were down here, so they could depend upon, that's right, Eli, they could depend upon growing their capital stock, capital per worker. This is small k, right? But now they've moved up from here. Now they're in here. And where are they headed? They're headed in this direction, and this is where it's flat. The function is flat. That's right. Manuel, right in there. Let me highlight Manuel's statement. Other people were saying the same exact thing. They have to shift. If you look into chat right now, look at Manuel's statement. They have to shift from a development strategy on developing their income per capita, right? That's what this term is, income per worker or output per person per capita. They have to move from a development strategy that was based upon investments increasing their capital per worker because they got big moves here. They're now in the middle and they're heading towards the flat part of the function. The flat part of the function, the rich countries have to depend upon technological change because the function is so flat. And the challenge for middle income countries like China, particularly, also Brazil and others in the middle, is to change. And the Chinese leadership knows this for certain. Okay? They have to change from having a development model that depended upon investment and capital accumulation here towards a model based upon rich countries' development, which is based upon rapid technological progress and rapid technological change. And that's a complete change in their viewpoint. The Chinese investment as a fraction of GDP in some years is over 40 and 50% of GDP has been plowed back into investment, building factory, machinery, equipment, cities, roads, a Belt and Road system, right? Airports, water ports, the Three Gorges Dam, that whole system. That is tremendous capital investment, capital accumulation, a tremendous amount of investment. That's what got them from being probably the poorest country in the world in 1960 out to the middle now. That now has to change. That's what this graph is saying. I hope your mind is getting blown. That's what this one simple graph is saying. Now the country now has to move towards a more technologically oriented development strategy. Okay, and that is a challenge for a country. Building apartment buildings and roads and bridges and airports and hydroelectric dams is a very different kind of expertise and process and concentration of your economy than technological progress, building a high-tech sector that's going to find the next new thing, that's going to find the next app, the next piece of software that's going to revolutionize the world. And your workers have to move from being construction workers, right, to being those kinds of tech, software, coding, tech workers. That's a complete change, right, in your economy's outlook. Development out. This is called development. As you move from poor to middle to rich countries, that's called economic development. And that is the challenge, right? And it's right here on the graph, right? It's right here on the Solow graph. Minds officially blown. Okay. Let me give you a picture. If you're following on the slides, I'll give you a picture. This is Shanghai in 1990, right? That's the Bund and the river and so on. Here's Shanghai in 2020. That difference here to here is due to investment, leading to increased capital and increase, of course, capital per worker, right? But that's done. It's hard to see how that city can be more built up. Okay, right? This movement says China, at least in Shanghai, right, is at the limit. It now has to move towards not investment, but move towards technological progress and reorienting its labor force, its education system, its entire market, its entire economy towards technological progress, because it's built itself out. Now, of course, there are other regions in China, central China, western China, rural China that don't look like Shanghai, of course. Shanghai and the coastal and southern China look like this, but the rural parts don't. And so there's still an element of, it's a middle income country after all. The slope isn't completely flat. And so investment still will play an important role in China, but it has to now, its leadership is thinking like this. Its leadership is thinking, how do we move China towards a technologically savvy and oriented economy? Okay. And all of that comes, right? All of that comes from that graph, right? That's why the Solow model is just utterly profound and respected by economists. Okay, all right. So I want to complete the Solow model. We just started it. We just have that one graph. There's many more graphs to come. Okay, they're coming. Right? They're coming. We want to complete the Solow model now, but the big surprise has come, right? It comes right out in the first thing, and it all comes from this shape. That's why I asked you to do this. It all comes from that shape, interpreting what that shape means for different groups of countries. Okay, but now to complete the model, we want to look at national savings. Okay, savings comes from investment. Investment comes from national savings. China is the world record holder for saving. No country has ever had a savings rate like China. Chinese savings rate sometimes is over 50, 55% of GDP. It's astonishing. No country has ever had anything like that. Okay. Here we're saying national savings, and that's capital S, here, is some fraction small s of real GDP. So small s here, I usually call small s like this because I can write it, okay, is the savings rate. It's the percentage of real GDP that is saved and not consumed. Okay. And it's a fraction between 0 and 1. In the United States, you may occasionally hear that the US savings rate is 4 or 5 or 6%. That's only one measure. Okay. If you measure savings properly in the United States, it's probably around 20% of GDP. Okay? Not the Chinese level of 50 to 55%, but it's about probably 20%. And here's the reason why. Many people, of course, save in savings accounts. That's just one way they put their money, they put the income that they're not consuming into a bank. But some of them buy stock, right? Some of them buy bonds, and some of them buy homes. And for the 60% or so of U.S. families that own their own home, right, that becomes their most important asset. Right? And repairing the home and refurbishing the home and mowing the lawn and fixing the roof, those are all ways in which they're plowing some of their income into their key asset they're saving. When you include homes as part of people's savings, which is certainly as much as true as a savings account, right? There's wealth in that home. Okay, there's wealth in that savings account. And when you take that into account, the U.S. savings rate out of GDP is something in the neighborhood of 20%, and that's the more appropriate way of thinking of national savings in the United States. But it's nowhere near the Chinese savings rate of sometimes 15, 55%. In any case, that's this variable S, and it multiplies real GDP, capital Y. Okay. If you're paying attention, what's the next thing I do in chat? What do I do next? Come on now. No, not yet, Katie. Not yet. Oh, so I missed the first comment. That's right. Yeah. Yeah, not yet. And I don't single it out. The next thing I do, so if you go back to what I said, the slideshow or the transcript, I'll introduce a variable, and the first thing I do with that variable is I divide by L. Okay, we always divide by L. Okay, and we'll turn things into per worker terms. So I'll divide by L, right? And then I get this. Here I'm dividing this side by L, and here I'm dividing this side by L, right? Here's my dividing by L. Over here, I have savings per worker, and capital Y divided by L, we know is small y. Remember, small y is defined as capital Y over L. Well, I know what small y is. Remember, small y is the intensive form of the production function. Looks like this. So if I put that in here, right, look what I get. And so now, right, I have another function, right? I have y is equal to f of k, which is k to the alpha, which we know is our favorite root function, right? It's small k and small y. And now I have this function. Remember, s is between 0 and 1, 20%, 30%, 50%. And so this has the exact same shape as the y function. It's just shorter. And here's savings. Okay. It's just a shorter function, right? It's only 20% in the United States. If the savings rate is 20% of income, then it's 20%. It's only 20% of the height of y. In China, it's 50%, so it's half as short as y. And here's the function. Okay. So here's our savings function, and here's the original output function. The output function has this shape, and of course, the savings function has the same shape. It's just, well, shorter. All right. So far, so good. We're building this function. All right. We only have one more graph, but it's we got to get there. All right. On this line. Okay. Next part. Consumption. Well, if we want savings, we want consumption. The consumption fund, we can call this the consumption function. Consumption, capital C. Okay. In the consumption function, we're saying consumption is that part of real GDP that you don't save. So you save this part and you consume the rest. Okay. And of course, the next step in chat, Katie, next step. Katie, divide by L. Thank you, Katie. Divide by L. Thank you. Divide by L. And I get small letters. Notice the small letter. Capital letter here, small letter here. This small letter small c, and that's how I'm going to write small c, right? I have to put a little tail on it. Small c is defined as capital C over L. Put a little tail on it to make it small c. Okay. So far, so good. And of course, I've divided this side by L and this side by L. Capital Y divided by L is small y. Okay. Which I can expand this. I'm going to multiply out that parentheses. So y minus s times y. The y function is the f of k function. Here's y, and this is f of k. The s times y is s times f of k. Okay. It's the difference between those two. What is that? It says the consumption is the difference between output and saving. So output gets produced. Okay. Some of it is saved and consumers eat the rest. Okay. Or another way of saying that is consumption per worker is the gap, right? This is a gap, right? Here's the y function. Here's the s of y function. The difference, it's the gap between those two functions on the previous graph. In other words, if we look at it, this graph, here's our savings function, here's our output per worker function. For any level of capital per worker, call it K, small k1, here's savings per worker. Here's output per worker, what gets produced. And this gap is consumption per worker. Because small c is equal to 1 minus s times y. It's the gap here. And if you were somewhere else out here at K2, consumption per worker would be at this gap, right? From here to here, okay? So consumption per worker is a gap, savings and output per worker are lines. All right, so far so good? All right, just check up with. I will say there's no money in this model, just for somebody who, there's no money here. I haven't, M, our symbol for money will be M. I haven't written M, okay? It's just goods and services. It's just things get produced, saved, and consumed. You consume goods, you make goods, and you save goods. Next, there's two equilibrium in this model, okay? That makes it a fancy model, okay? I don't want to talk about those equilibrium. There's a static equilibrium. A static equilibrium means an equilibrium that holds at every single moment in time. Remember, our model is a very long run model. It's a model of 30 to 100 years. So there's lots of time, okay? Every single instant over this 30 or 100 year period, the static equilibrium holds all the time. You know this equilibrium, and when I do it on the next slide or two, it'll be straightforward for you, okay? But there's also a dynamic equilibrium, because remember, this is an equilibrium over time, okay? That the economy will be going, I don't want to use that arcing thing, it'll be going to an equilibrium in the very long run. It may not get there this year or next year or the next year or 10 years, but somewhere between 30 and 100 years, it will get to its dynamic equilibrium. We have a name for that. That dynamic equilibrium that will eventually be achieved in the very long run, in 30, 50, or 100 years, is called the steady state. Sometimes I'll use the abbreviation SS for steady state. It's sometimes by some researchers called the balanced growth path, the BGP. It's a path that the economy is now balanced on, is in an equilibrium, okay? For the Solon model, we'll use the notion of a steady state, okay? It eventually goes to a steady state over the time frame of 30, 50 to 100 years. So that means that this dynamic equilibrium will hold in the very long run, okay? 30 to 100 years, right? Let's start with the static equilibrium. Do this on the next page. The static equilibrium is the one you learned in Econ 2. Okay, it's very straightforward. You'll be reminded of this as soon as I've got it. Okay, and it says the following: okay, that y is equal to c plus I plus g plus net exports. Okay, that real GDP here will be purchased partly by consumers for consumption, partly by businesses and business investment, partly by government or government spending on goods and services, and partly on net exports. Some of these goods that we've produced will be exported and others will be imported. That's net exports. This is the famous equation from Econ 2. It's called the National Income Accounting Identity. Okay. Consumption plus investment plus government spending equals real GDP every moment in time. Okay. We're going to have to simplify this. Okay. We'll reintroduce some of the variables, but we're going to have to simplify this. And our simplification will take the following form. We're going to set G equal to 0 and net exports equal to 0. Okay. The idea here is you have to walk before you can run. Okay. You have to do the simple things first before you can put in the complex things. All right. We will reintroduce them in some later on, but at the moment we have to set those equal to 0. That means we just have consumption and investment. That's the private economy. Consumption is what households eat and consumed in a given year. Investment is the business purchase of factory, machinery, and equipment capital, right? That's business investment. There's no international trade and there's no government sector in the setup. All right? So that keeps things simple because the model will be complicated enough, I guarantee it. All right. So that means we have this function. All right. What's my next step, Katie? Katie, what's my next step? Thank you. Thank you. I'm going to divide by L. And how do I write that? If I let Katie off the hook here, how do I write that? If I divide by L? Someone tell me in chat what the formula looks like. Okay, that's right. I divide both sides by L. And what does it look like? Yeah, write it out for me. Not that. Yeah, there we go. All right. If you're dividing by L, it should be small y is equal to small c, look at my tail, plus has to be small I. Okay. All the small letters mean in per worker terms. Okay. Get it? You have to have that notation, or else there's a difference between capital Y and small y, a difference between capital C and small c. Small c is consumption per worker. Small y is output per worker, or GDP per worker. And so here's the function. Okay. Next step is, I know what C is. I know the C is a consumption function like this. We just did this on the 2 slides ago. Okay. All the GDP that isn't saved is consumed. Right. And so I can put this into this function. Substitution gives me that. And then notice I have a y over 1y over here, and this will be a 1y, right? Because when we multiply through the parentheses, there's a y there. And those two will cancel. And so simplifying, if these two cancel, this one and just that one cancel, and I put the sy on the other side, I get this expression. That's a key expression, okay? That says savings per worker is equal to investment per worker, okay? Savings is equal to investment per worker. This is the fundamental macroeconomic equilibrium condition. This is in every single model we will do this term, and all macroeconomic models. Okay? It says the following: if you're going to produce GDP, and some of that GDP is go to investment, right? Remember what investment is. It's not purchasing stock and bonds. Investment is the purchase of new factories, new machinery, new equipment, and new homes. If you're going to produce GDP, and some of that GDP is going into a new home or a factory, then that must be GDP that wasn't consumed by households. It must be GDP that was saved. The only way your economy can have resources to build a new factory is if consumers didn't already eat those resources as consumption. Okay. It's the key macroeconomic equilibrium found in every model we do, and every single model in macroeconomics. Okay, in order to have resources to build a new factory, those are resources that can't be consumed by somebody else, by households. Okay. In fact, when we get to the end of the course and we talk about the short run of the economy, we'll have an entire graph called the investment savings graph. And everywhere along that graph, okay, savings will be equal to investment. That is the static equilibrium, all right? That savings is equal to investment. So just going back, the static equilibrium starts like this. We simplified it a bit, but it ends up like this. Okay. Now the dynamic equilibrium. That's hard and fun. Okay. This describes how the economy changes over time. Okay. That's what that's why dynamics mean over time. So let's take a look at how this works. In this model, in the Solow model, the key macroeconomic driver of the entire model is small k. That's the, when we graphed our function, right? Small k was here, small y was here, and we had this shape, right? So, and I started doing this, right? The changes in small k, capital per worker, were what drove, right, output per worker, right? That's the driver. That will drive everything. It drives savings, because savings is the shorter function. It drives consumption, because consumption is the gap between those two. It drives, small k drives everything. So we need to know and understand how small k evolves over time. Okay, let's do that. The term small, the variable small k, you recall, is capital K divided by L. Okay, so if we need to know how small k changes over time, we need to know the time derivative of small k. Recall what is this k dot thing I have here, right? That's what we have here. Recall what k dot is. It says how small k changes over time. It's the time derivative of small k. It's the derivative of k over L, okay, with respect to t. And that will give us the model's dynamics. Well, we're differentiating in the numerator here. We're differentiating k over L. That's a quotient. And so that means we'll need to use the quotient rule when we differentiate. Okay, this is a quotient. And when I use the quotient rule, recall what the quotient rule was. It's in the math review and possibly on the Canvas quiz this weekend. Some of those rules may be on the quiz. The quotient rule says it's the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator all over the denominator squared, right? All over the denominator squared. Just looking to see if everybody's with me. Edwin and so on. Okay, Alexander. Good. So I'm going to take this derivative here, and that's it. Okay, notice the dots. Make the dots a little bit bigger. Right. There's the denominator squared part right here. Okay, that's in, right? Because L is in the denominator here. And I have L, which is the denominator times the numerator. The numerator is K, right? So I'm looking at K dot. I'm taking the derivative of K with respect to time. That's K dot minus the numerator, which is K, and that's capital K, times the denominator, right? The derivative of the denominator, that's a dot there, all over the denominator squared, right? I'm going to rearrange this. I can simplify this. I can divide L squared into both parts of the numerator, both terms in the denominator. That's a dot. It's not I dot, it's L dot. Okay. Yeah, eyes have small eyes always have dots, so I can't help that. Okay. Here, any dotted variable is a time derivative. Okay. That's the notation by the time derivative. A dot variable, so anything x dot is equal to dx dt. Okay. If you want to brag to your parents, you can say that you're using the rules and notation of Sir Isaac Newton. He developed this notation because he didn't want to write out the dx dt parts. So I'm going to simplify this expression, and I can simplify it in this way. Okay, if I divide L squared into both the first term and the second term, well, one of the L's cancel, and I get K dot over L as the first term. And on the second term, the term after the minus sign, I can write that as K over L times L dot over L. Notice I still have an L squared in the denominator, but I've rearranged it into a more interesting way. Okay, and notice what I have here. What's that variable I just put in parentheses? That variable I just put, that's small k. That's right, Luke, that's small k. So I can rewrite this as this term here. I haven't done that yet, but I'll rewrite it as. Okay, so that's, now things are starting to look, well, a little bit cleaner. They're certainly looking cleaner than that. Okay. Now here's an assumption that Solow makes. I want to explain this. Solow presumes that as soon as a person is born, they go to work. Okay. So that's kind of a depressing model, right? In other words, there's no teenage years, no childhood. As soon as a worker is born, you got to work. Okay. On the other hand, nobody ever dies in the model. As soon as you're born, you live forever. So that, that's a good thing. Right? We could certainly handle death, right? But that would be a complicating feature of the model. And, we're just building the model now. We have to walk before we can run, okay? We could certainly handle death, but let's just stay with what we're going here. The number of workers, no, if you have more and more workers, they make the output. Output is produced by workers. Right? Nobody dies, okay? And you're born as a fully formed worker, no teenage years, no childhood. So then the growth rate of labor will be the growth rate of the population. Okay, as the population grows, the labor force grows in the same rate. That's in fact roughly true for most modern economies. Okay, the growth rate of the labor force is equal to the growth rate of the population. Well, the growth rate of the labor force should be our symbol G sub L, which is L dot over L, and we have L dot over L here. And now we're just going to make a simplifying assumption that L dot over L is equal to the parameter N. Okay, just to make it simple. Okay, N stands for newbies. These are the new workers being born. They come into the model. Right? They're born into the model. They could also come from immigration. That's perfectly fine. Okay? It could be people having babies through natural fertility, or immigrants coming in. It doesn't matter which way. In the United States, when we look at natural fertility rates, people having babies plus immigration, that's right around 1% per year, that the U.S. population and the U.S. labor force grows at about 1% per year. In other words, N is about 0.01 or 1%. And that's going to replace this L dot over L part. And so then the formula becomes quite much simpler, okay? Small k dot, which is the time derivative of small k, is equal to capital K dot over L minus N times K, small k, okay? So we started with a complicated function and now have derived a somewhat simpler function, right? So next, I'll deal with this capital K term in the numerator. Now I'm going to push on here, okay? And we'll ask ourselves, how does this capital K change over time? What determines, right, capital K dot? Okay. Any answers to that in the room? How does capital K change over time? I've actually mentioned this a couple times already. How does the capital stock increase? Investment. Yeah, investment, right? But we got to be careful here. We have to be a little more subtle. Yes, it's investment, but remember the time frame we're looking at. 30, 50, 100 years. Yeah, that's right, Arya. Um, Over 30, 50, and 100 years, right, capital will fall apart. That's called depreciation, and we should take account of that. And so, yes, capital increases due to investment, right? But we also want to take account of depreciation. Capital depreciates also. In other words, investment will increase the capital stock, but depreciation will decrease the capital stock. In other words, machinery and equipment fall apart. Okay, every year there's a little bit of deterioration in every piece of machinery in every factory. It kind of is new at the beginning, and it gets older and falls apart, just like us. Okay, and so here's what we'll call depreciation. Depreciation will be delta, and this is the small delta. The Greeks had upper and lower case letters, just like we do. That's small delta. Small delta times K is the total depreciation, where small delta is the depreciation rate. Okay, and we'll be looking at what's called straight line depreciation. So what we mean by straight line depreciation is the following. If a piece of machinery falls, 10% of a piece of machinery falls apart every year. So you start with 100%. After a year, you've only got 90%. After another year, you've only got 80%. After another year, you've only got 70%, and so on. At a 10% straight line depreciation rate, then at the end of 10 years, it's gone. There's no capital left. Okay, that makes sense to you? If the depreciation rate, straight line depreciation rate, delta, is 10%, okay, then 100% of the capital stock will be gone in 10 years. Let me just do another exercise. Suppose I told you that 4% of the capital stock falls apart every year, and we're using straight line depreciation. How long does the capital stock last? 25 years. So 4% falls apart every year. After 25 years, 100% of the capital stock has fallen apart. In other words, the capital stock no longer exists. Okay, we call it simple depreciation too. Okay, just keeping things simple. All right, that's the idea here. And so then, okay, we can make the following statement. Okay, that capital increases, in other words, capital K dot is positive if investment exceeds depreciation. Okay, if you paid off the depreciation and there's something left over, whatever's left over goes to increase the capital stock. That's the logic of it. And so that formula is that's the statement here is exactly this formula. K dot is equal to investment minus delta times K. Here's the investment, and here's total depreciation. If this is positive, investment is greater than total depreciation. Right? And then the capital stock can grow. And that gives us an expression for capital K. From the previous page, we had this expression. That was the simplified expression on the bottom of the last page. And all we're going to do is take this and plug it in for this term. Let's do that. All right. The substitution gives us this. And notice, Katie and others, we are dividing by L, just like I said we would. We introduce a variable and we divide by L. And we are now dividing by L. And then remember, when we divide by L, we create small letter. The variables become small letters. Okay, so those small letters are the following. Yeah, I know this little dot doesn't mean this little dot doesn't the time derivative. Sorry, that's the only way we can do this here. That's investment per small I here is defined as investment per worker. Okay, and we have this term here becomes delta times small k, and we have this term here repeated n times small k. And now I'm just going to rearrange variables, and I have this expression here. Small k dot is equal to investment minus delta plus n times small k. So I'll start the next slide on this. That's the dynamic equilibrium equation. We can do a little bit more with this. Okay. We'll do a little bit more with this. Recall that the static equilibrium says that savings is equal to investment in per worker terms. So I can replace this small I with S times small y. And so I get this. And remember that small y is equal to F of small k is equal to k to the alpha. So I'm going to make those two substitutions here, right? S times y is F times k to the alpha. I'm sorry, S of F, F of k, or k dot is equal to S times k to the alpha minus delta plus n times k. This is the one we will mostly use. This is the other one. These are the dynamic equations of the model. I don't want to say I want to call them I might as well call them by their true name. These are differential equations. They are differentials. K dot, recall K dot, small k dot is equal to dk dt. So on the left-hand side, I have a derivative, and a derivative is some kind of formula here. Okay. Both of them have a name, and their name is the equation of motion of the capital stock per worker. Okay. That's how the capital stock per worker evolves, right? And that's important because that is the variable on the horizontal axis that's driving everything. This variable drives everything, and these equations tell us how this variable changes. And when small k changes according to k dot, savings will change, output will change according to these other functions. So I want to finish up this section in a couple of minutes to describe the dynamic equilibrium, which is called a steady state. Okay. A steady state, the definition of a steady state that Solow gave us is the following. Some key macroeconomic driver grows at a constant rate. Okay. The idea is the following. We don't, over the time of 30, 50, 100 years, things don't blow up. Right? Output per worker doesn't go to infinity. It doesn't go to zero. Even in Argentina, it didn't go to zero. It flattened out, but it doesn't go to zero. It doesn't go to infinity either. Right? It's relatively stably growing. It's growing at a roughly constant rate. Okay. So the definition of the steady state is some key macroeconomic driver grows at a constant rate. Well, the key driver is K, and its growth rate is K. It's growing at time K dot. Okay. The question is, what constant rate? Okay. Solow says the following. The constant rate is zero. Let's set it equal to zero. If you set it anything different from zero, you have to explain why. If you set it equal to a constant 17, well, why 17? Okay. Zero makes some sense in that if something's growing at a zero rate, it's constant. Okay, that makes some kind of sense. And that's what he says. So we'll take him at his word. He's smart. He's smarter than us. He's a genius. Let's see what he gets out of this particular assumption that the steady state is where some key macroeconomic driver grows at a constant rate. The key driver is small k. So let the growth rate of small k be equal to zero. We know the growth rate of small k is k dot over k. If that's got to be zero, it must be the case that k dot is equal to zero. And recall, we know that k dot from the previous slide is S times k to the alpha minus delta plus n times k. And if this thing's equal to zero, right, then this whole expression is equal to zero. Then we can set the two sides here equal to zero, equal to one another. That the savings function here is equal to this thing here, okay, whatever this thing is called, or S times k to the alpha is equal to this expression. Okay, S times k to the alpha we already have on the graph. Here's y is S times y, which is S times k to the alpha. So this is on the graph already. What is this thing? That thing is a straight line. It's a straight line that comes out of the origin and has slope delta plus n. And you can see that there's an intersection. There's a place where the two of them, I think a different color, it's a place, come on. There's a place where the two of them are equal. That's the steady state. Okay. And so if we do this, here's the steady state right here. Steady state is where k dot is equal to 0, or s times k to the alpha is equal to delta plus n times k. Here's the savings function. Here's this line. They're equal here. That's the steady state. Here's the steady state level of capital per worker. Here's the steady state level of output per worker. Sometimes I'll call this Y star. Sometimes I'll call this K star. I prefer the stars. And we know the gap between these two may be a different color. The gap here is consumption per worker. And so we've solved for the steady state equilibrium, okay? A dynamic equilibrium. The economy will go to this point. And I want to, at this point, I want to take a few minutes break. We'll take a 10-minute break here. We'll take a 10-minute break. So I have 2:53. We'll come back at 3:50. Oh no, at 3:03, and we'll pick up the thread here. And I'll take a break. I'll keep the meeting on, right? But I will take a break. I'll get a double espresso, and I hope you get a revitalized with some water or something else. So we'll come back and talk about extensions of this Solow model, what this equilibrium means. Okay, so I'll see you in 10 minutes.
Oh, excuse me, Professor, we can't hear you.
Yeah, I get it. Okay, that I heard. How about now? Okay. All right. Thank you, Luke. Okay, bueno. uh, okay, so if you know about Zoom, it's a little funky on the audio. In any case, I want to talk about this, the function we ended up with in its general form. What's on this graph and where we can identify it. Output per worker is the small y function, okay, and it's on this axis, output per worker. We could also call it income per worker. We could also call it average productivity. Because look at it, it's y, capital Y divided by L. That's what small y is. It's the amount of output divided by the number of workers. Right? It tells us what the average worker is producing, their average productivity. Okay. That's the y-axis, the productivity of the labor force in the country. The next is savings per worker. These are resources that, by definition, have not been consumed. So households have eaten some things. We know where that is. Households have eaten any distance between these two graphs. That's consumption per worker, the little tail on it, right? This part, for this capital stock here, must be the amount of output that was produced that was not consumed. That's output that's available for investment. And so the remaining line, this line here, which is a ray right out of the origin, it has a slope equal to delta, which is the depreciation rate, plus population growth, okay, which comes from natural fertility and immigration. Okay. That has to be somehow kind of like an investment line. If this is savings and this is the steady state where it intersects this line, that has to be some kind of savings line, investment line. And we call it break-even investment. That is the following. Take the delta part first. There's some capital that's falling apart every year at rate delta times small k. Okay. That has to be replaced, or else the capital stock will shrink. In addition, that's the plus sign, there are some newbies coming into the economy every year. Okay. new workers being born, that's natural fertility, and new people coming into the economy as immigrants. Okay, those newbies, when they come in, they have to get the same capital as everybody else. Okay, that would only be fair and equitable and equal. And so if you're going to do savings, right, and you're going to kind of stay still at the steady state, you're going to stay steady, then you have to do enough savings so that you give enough investment to cover what's falling apart. That's the depreciation part. Plus, to give the newbies the same capital that everybody else has. That's the end part. And if you do exactly that, and no more and no less, then you're right here. And you've done enough savings to cover what's falling apart and enough savings to give the newbies who are entering the economy as workers the same capital as everybody else. And there's nothing left over, so you'll be steady at a steady state. That's the logic of that intersection. Okay? Or savings, one way of saying it is to say is savings per worker is equal to break-even investment. And mathematically, that says S times K to the alpha is equal to delta plus N times K, or that K dot is equal to 0. All of those are true right there. Okay. Well, we can solve this. This is how we solve it graphically. We can also solve this model mathematically, and that's on the next slide. Let me show you a numerical example. Okay. First, we suppose that there's a production function that's Cobb-Douglas with constant returns to scale. That's part of what Solow starts with. The capital share is 50%, capital share of GDP. Immediately from these two things, right, notice these is, in a way, it's a numerical example, but the way I'm setting it up is as a word problem. And so the logic here is you have to turn this word problem into, well, a numerical example. These two pieces of information, production is Cobb-Douglas with constant returns to scale. That says Y is equal to K to the alpha, L to the 1 minus alpha. The second part, the capital share of GDP is 50%. That says what? That alpha is equal to 50%. And so the production function becomes K to the 1/2, L to the 1/2, or K to the 0.5, L to the 0.5. Okay. And we know from this, if we start like this, the intensive form of the production function will be K to the alpha, which will be K to the 1/2, small K to the 1/2, or K to the 0.5, small K to the 0.5. Okay, so each of these steps will be in words, and you turn this into mathematics. The next part, national savings is 20% of output. Okay. What letter is being described here? It's national savings as a percent, not big S, small s is 20%. Is small s is equal to 0.20. Okay. Next, the capital stock falls apart on average in 25 years. What's being described here? What variable is being given here? Someone? Depreciation, and that's right, Angela. And what is the depreciation rate? Not depreciation, but the depreciation rate. That's right. And what is the depreciation rate? That's right, Luke, 4%. Okay. Next, population growth is 1% per year. That's N. Okay. So each of these is being given, and then we can put this together. Okay. Find the steady state values of K, Y, and C. All right. So putting these together, that is, we have the following. Okay. Alpha is 50%. That's alpha. The savings rate is 20%. The depreciation rate is 4%. And population growth is 1%. All expressed as a decimal. Okay. Putting this together, here's the output aggregate production function, right? Notice the alpha here. Continuing over here is half. Dividing by L simplifies to the aggregate production function to the intensive form of the production function. Notice we have a half here, and it is reproduced. It's still on that exponent. Okay. Next, in the steady state, K dot is equal to 0, or from the graph, right? Here's the savings function. Here's break-even investment. Delta plus N times K. That's where the steady state exists. And so we'll set those two equal. We have all these parameters now, S, alpha, delta, N. We can solve this for K. I plug those expressions in here. I get 0.2 times K to the alpha is equal to 0.05, the 4% depreciation rate, plus the 1% population growth rate gives us 5%, or 0.05. Okay, and I can solve this. Okay, notice there is a solution. This expression is solved at 0, right? If K is equal to 0, that's a solution. Of course it is, because savings does equal break-even investment at 2 points. It equals it here, but they also both come out of the origin. This one's not very interesting, so we'll ignore it. Okay, but with this expression, I can solve for small k. And once I have small k, I can get everything else. So if I solve this for small k, I'll divide through by 0.05 and get 4 is equal to, and divide through by k, k to the half, and get 4 is equal to k to the half. So k is equal to small k is equal to what? What is it equal to? 16. That's right. Got to be careful. Got to square it. I think the square root got to square it. So small k is equal to 16. If small k is equal to 16, then we can solve everything else. All right, from the production function right here. Once we have small k, we can get small y. Small y is 4. Once we have small y, recall that C is equal to 1 minus the savings rate times small y. And so we have this. The savings rate is 20%, so the consumption rate is 80%, right here. And 0.8 times 4 is 3.2. And so we have all of the variables we want mathematically. On the previous slide, we had them graphically. All right. So that's how you solve out the model. Okay. Let's work with this model a little more deeply and go into greater detail now. Okay. What we're solving for, we get this expression here, K dot is equal to S times K to the alpha minus delta plus N times K. That's the general solution. That's the differential equation, or the equation of motion of the capital stock per worker. We know in the steady state, K dot is equal to 0. When K dot is equal to 0, that means savings per worker is equal to break-even investment. And that's right here. That gives us K in the steady state, small y in the steady state, consumption in the steady state, and this, of course, would be savings in the steady state. Come on. I don't know why it didn't go through there, but it didn't. Okay. And my pencil is, how much charge I have in my pencil? 99%. Okay, in any case, to go into further detail in this model, right, we want to ask ourselves, is this model stable? Okay, is this equilibrium, which occurs right here, is this steady state stable? And what we mean by a stable equilibrium is when you change it, right, for any small change, does the model come back to that point, or does it go off to infinity or go off to zero? Okay, that's what we mean by stable. So for instance, I don't know, if you have, I have a DVD here. If I put a DVD like this, I guess you can't even see that. This is my DVD. It's about Ansel Adams. If I put it there, that's not a stable, I can't even make an equilibrium on it. It's not kind of a stable equilibrium, because if I don't know if you could see that, if I change it, if I change the equilibrium, I'm going to fall off. But this is more stable. All right. Now, if I make small changes, it does tend to come back to that equilibrium. Okay? So that's what we're going for here. Is this, and we'll learn something about how the economy operates, how the Solow model operates, by thinking about whether this is a stable equilibrium. Here is the steady state, K star. Suppose, and we have the K dot equation is equal to S times K to the alpha minus delta plus N times K. Suppose the economy was shifted, pushed off this steady state from K star, and it was pushed down to K1. Okay. Is there a process, a mathematical process, a graphical process, and an economic intuition process that would tend to push the economy back to K star in this direction? Or would there be a process that would send it in this direction? That's what we're asking when we're asking, is this a stable equilibrium? So let's take a look at this. Graphically, what happens is the following. Okay, at K1, if we get pushed down to small K1, the capital stock per worker is smaller than the steady state level. This is break-even investment. But here is saving. Okay. And here's the gap between the two. Well, notice that break-even investment is less than saving. If break-even investment is less than saving, this is break-even, and here's saving, then it must be the case that K dot, small K dot, is positive at that point, because savings is higher than break-even investment. And K dot is how small K dot is how small K changes. So K dot being positive means K goes in this direction. And we know exactly how much it goes. This is the gap between the two. So it has to go by that much. If this vertical gap is this horizontal distance, then it has to go to K2, and we got closer to K star. In other words, the economy moves back towards its original steady state, which means, okay, that this steady state was stable from below. In other words, if you have something like this and you change it a little bit, it goes back to its equilibrium. Okay. Of course, at K2, we could do the same kind of analysis. Break-even investment is there, savings is here. Okay. And so it's still the case that savings is greater than break-even investment, and K dot is still positive, which means you get closer still. You move closer and closer. What is the, that's the mathematics, that's the graph. What is the intuition? Right? Well, at a point like K1, the intuition is the following, okay? The amount of saving you need just to break even, the amount of saving you need to cover depreciation plus population growth is right here. But you're doing more saving than that. Your saving is up here. So you've got extra saved resources that can go to increase the capital stock per worker. You're not standing still anymore. You've saved more than is necessary just to break even. Okay. And so that the extra amount that you've saved can go to increase everybody's capital stock, the capital stock for every worker, the capital stock per worker. What about over here? Suppose we start, I'll start over here. Here's again a new graph. Here's K star. Suppose you start out here, K3. And we know that K dot is equal to S times K to the alpha minus delta plus N times K. What's true at K3? What's the sign of, all right, put it this here. At K3, K dot, what's the sign of K dot? Small K dot. Tell me in chat. It's negative. That's right, Angela, negative. You can see that if you, at K3, we bounce up here. Here's saving. That's this part. But here is break-even investment. And in this case, break-even investment is greater than saving. Well, that break-even investment has a negative sign on it. And so K dot is negative. Well, if K dot is negative, okay, that means the capital stock per worker is going negative. It's going in this direction. Okay. And if it's going in this direction, notice it's going back to the old steady state K star. And so the equilibrium is stable from above as well. In other words, either way, if you've got a steady state here and the economy is pushed a little bit beyond the steady state or pushed a little bit short of the steady state, the economy tends to come back to the steady state. That is, the steady state is stable. You pushed on one side, it'll come back. You pushed on the other side, it'll come back to the same steady state. Recall that this equation here is a differential equation. And in the language of differential equations, that means that K star, which is the steady state, is a sink, right? That is, no matter where you are, right, on this graph, you are sucked down back into the sink, back to K star, from this side or from this side, okay? And the economic process from above is kind of interesting, okay? We've done the graphical representation. I use this equation of motion of the capital stock, the differential equation, to interpret how small k dot is negative. And here's the economic intuition, okay? At K3, savings is insufficient to cover break-even investment. You're not doing enough savings to replace either what's falling apart or the newbies coming in who need capital stock. So let's think of this as being, the reason the break-even line is so high is because there's lots of depreciation. Lots of things are falling apart. Okay, and you're not doing enough savings down at K3. You're not doing enough savings to cover that. Well, if capital stock is falling apart and you're not replacing it quickly enough, then the overall capital stock per worker must shrink. Okay, that's the idea. And sure enough, it does shrink back to the steady state. If, on the other hand, the reason the break-even line is so steep is because at K3 is because N is too big, then that means lots of newbies are coming in. They're either coming in through immigration or natural fertility. They're being born as workers. And you're not saving enough to give them enough capital that everybody else has, the same amount of capital that everybody else has. Everyone else has capital K3, but you didn't save enough for these newbies coming in. And so when they come in, they'll get a lower level of capital than everybody else has. And if they come in and they get a lower level of capital than everybody else, then the average capital stock will fall, because the old workers, the incumbent workers that are already existing, they'll have K3. But the new ones coming in and save enough for them, and they'll have a smaller amount of capital, smaller than K3. And when you average those two groups, the capital stock over the entire country, capital stock per worker over the entire country will be lower. And that will move you in this direction for both reasons. Okay? So this economy, the steady state, is stable. And we learned something about how this differential equation and how savings and break-even investment are related to one another. All right. I want to do what are called the comparative statics results, the implications of the model that we've built. We've got the model, now we have to do something with it. Okay. And what's curious about these comparative statics is what we're going to do is we're going to change some of the givens in the model, okay, and see how the model performs. What's curious about these comparative statics is that Robert Solow did not build the model to generate comparative statics. He built the model to explain the Kaldor-Great ratios, which it does, but I'll leave that off for a few minutes. But it turns out the comparative statics results that come out of the model hold quite well in the world. And so the idea is the following: if a model is built to do one thing, reproduce the Kaldor-Great ratios, but it also does something over here that it was shows you something interesting over here that it was never built for, and it's true in the world, then you know you're dealing with a very important and useful model. And it's built to do one thing, and you better do that one thing, but it also tells you something else. That's a powerful model. Okay. So what are the givens? If you look back to the numerical example, I had to give you the following things. I had to give you alpha, the capital share. I had to give you the savings rate. I had to give you the depreciation rate, delta, and I had to give you the population growth rate. I also gave you that it was Cobb Douglas with constant returns to scale, but that's not so interesting. Okay. Now, if we look at these, the capital share, alpha, the savings rate, depreciation rate, the population growth rate, there's two of these that really don't change very much, or can be changed very much, and that's alpha and delta. Alpha, the capital share, as I've mentioned, is stable in most countries. The US capital share has been 30% for the last 70 years, roughly 30% for the last 70 years. And the labor share has been roughly 70% for the last 70 years. It doesn't change very much. And that's true for most countries, not all countries. The second one, delta. Delta is the depreciation rate, how fast the capital stock falls apart. That really doesn't have much of an economic motivation, cause. It's mostly about engineering and the climate, right? In the tropics, things fall apart more quickly. It's hotter and it's moister, and that tends to depreciate machinery and equipment more rapidly. But there's very little economic reasoning behind depreciation. So the only two that are likely to have economic consequences are changes in the savings rate and changes in population growth rate. And that's what we'll look at. Okay. When there's a change in the savings rate, what happens in the economy? When there's a change in the population growth rate, what happens in the economy? Okay. That's the logic of it. All right. So first we'll talk about population growth increases. So N rises. Right. Well, first we have to ask, where does N live? N lives in the break-even line. So we'll want to look at that. Here's N. And if N2 is higher, the idea here is N2 is higher than N1, then the break-even line gets steeper. And rotates in it. They both have to come out of the origin, always, because if K is equal to 0, there's no break-even investment. So it rotates, well, we would say that counterclockwise, in the opposite direction of a standard clock. Okay, and notice the steady state would go from here, this would be steady state 1 at K1 star and Y1 star to a new steady state here, steady state 2, K2 star, Y2 star. And the economy would transition, here's point 1, here's point 2, it would transition along here. Okay. As the capital stock per worker fell, and recall the reason why the capital stock per worker is falling, there's many more workers. Okay, the population growth rate, either through natural fertility or immigration, is expanding the labor force. There's the same savings rate, right? And so there are more and more workers, in a sense, in the denominator here. Okay, because N2 is higher than N1, there's going to be much more population, much more L in that denominator. The capital stock per worker will shrink and output per worker will shrink. Okay, that's the idea. And what we want to do, that's the way the model works. We want to take this to the data. We want to see, is that true in the world? Right? And now here's the difficult part about this, or the interesting part about this, when you take a model to the data. In actual economies, if you're looking at just the United States economy, the United States economy does not have sufficient fluctuation in the population growth rate over the course of 30, 50, 100 years. US population growth rate has fallen from about 1.8% to about 1% today, just under 1% today. That's a very small fall. It's less than 1%, 1 out of 100. There's not enough variation in that number, right? And so what's been done is, instead of looking at one country and its different population growth rates, different ends across a long time frame, we look at the data internationally. Internationally, there is a sufficiently wide distribution of different population growth rates. Some countries' population growth rates are up at 4, 5, 6% per year. Other countries are quite a bit less than 1% per year. And so that's a sufficiently wide range of population growth rates. And this model says countries with high population growth rates, such as N2, would have relatively low levels of output per worker, and countries with relatively low population growth rates, like at N1, would have relatively high levels of income per person. And here's the data. This is the international evidence. Right? Does the international evidence reject the Solow model? Take a look at this evidence. Here's the population growth rate, and for a variety of countries, about short of 100 countries, 90 countries or so, on average from 1961 to 2010, so 50 years, certainly within the ballpark of our model. And here's income per person. This is Y over L in 2010. Does this evidence reject the Solow model? Does this evidence contradict? Somebody in chat, tell me this. Does this evidence contradict the Solow model? What do you think? Anyone? No, why not? If it doesn't reject, the answer here, no. If it doesn't reject, then it sort of confirms that if we look at this, this is a scatter plot. If we look at this scatter plot and I put in a best fit line, we talked about the best fit line last time, an eyeball line, I would put it in about there, right? And that line has a negative slope. And that negative slope means the following. Countries that have higher population growth rates, from 1% to 3%, say the United States to a country like, I don't know, Cambodia or so, you're moving from a relatively high level of income per person to a much lower level of income per person. Y in the US, small y in the US, small y in Cambodia. And so as n increases, small y falls internationally. And that's exactly what this says. As n increases, output per worker falls. And so the international evidence does not reject the Solow model. In other words, in common parlance would say, it confirms the Solow model, in part. Okay. How about the other variable, savings rates? Let's take a look at an increase in the savings rate. An increase in the savings rate is an increase in small s. But an increase in small s means that savings function, s times y, would shift upwards to s2 times y. And if we've done a good job building in this model, if you can picture it, if you picture the model, here's the break-even line. Okay. If we move from point 1 to point 2, we should move to a higher level of capital stock per worker and a higher level of output per worker. So if the savings function increases, this function shifts up. Here's the original steady state, 1, a capital K1, and output Y1 star. And the new is here. This is the new steady state 2, a capital per worker K2, small K2, and output per worker slightly larger, that's small y2. And so we would have the following relationship. Here's S2 is greater than S1, right? And this would lead to K2 being in the steady state, being higher than K1 in the steady state, and output Y2 in the steady state being greater than output Y1 in the steady state. Okay. And so as the savings rate increases, we would say steady state Y would increase. At a decreasing rate, you can see that's the famous function, right? We have a lot of increase in capital, but a smaller amount of increase in output per worker. Let's take a look at the international evidence. Does this international evidence reject the Solow model's claim about the savings rate? Okay, we have Y over income per person here, Y over L. And here, well, wait a second. We have investment as a percentage of output. Did I get this wrong? I mean, we were just doing savings, right? Is this wrong? No, because remember, savings is equal to investment. Okay. So this is still can be thought of as the savings rate. And in this case, the graph is up, the best fit line or eyeball line is upward sloping, which says that countries, other things being equal, countries that have higher savings rates also have higher income per person. Or that is, countries such as Rwanda here, savings rates quite a bit less than 10%, have a low level of income per worker. Countries in the mid-20s, like the United States here, have relatively high levels of income per person. And that's the answer here would have to again be no. If the international evidence does not reject the Solow model, then it supports the Solow model. Okay. And so Solow built his model to explain the Kaldor Great ratios, but it tells us other things. It tells us that countries with higher savings rates will have, other things being equal, higher capital per worker. And if they have higher capital per worker, they'll have higher output per worker. And that is true in general. There are extreme cases, Cape Verde out here, Luxembourg here, but the general average, right? That's what this regression line is telling us. The general average relationship is positive, okay? And for most countries, right, an increase in the savings rate, increasing the capital stock per worker in the steady state would increase output per worker, all right? So the Solow model was very successful in explaining this international evidence, part of the power of the Solow model. So having said this, I want to turn our attention to the last topic in chapter 8, okay? and the consideration of whether there is a best steady state on this graph. Okay, we look back here. In this case, we have two different savings rates and two steady states. Is there a way of saying that one of these steady states is better than the other steady state? That's the idea. Okay. Is there a best steady state? There are many steady states depending upon the values of alpha, the savings rate, the depreciation rate, delta, and population growth rate. Is there one in this whole graph, in this whole map, that's best? Solow says there is. Okay. Solow says that the best steady state on this graph will maximize consumption per worker. That's probably not what you thought. Okay, you may have thought that the best steady state would maximize income per worker. Okay, but that can't be true. You really don't care about your income. Most people don't care about their income. You care about your consumption that income can generate. Okay, well, let me give you an example. Suppose you lived in a weird country where, yes, you made a very high income of, say, $100,000. That's 30% more than in the United States. You had a very high income of $100,000, but the government taxed you at 90%. So the government taxed you at 90%. That's $90,000 of taxation. You would only have $10,000 left over for consumption. So though you had a very high level of income, because your consumption was very low, okay, you would be not very well off. Right? That highlights the point that people don't really care about the income, they care about their consumption. And the best steady state will be that steady state that maximizes the average person's consumption per worker, what we call small c. Okay. And that's a maximization problem, but it turns out it's not an easy one, okay? But it has some profound political implications as well that are coming up. So Solow calls this particular steady state that maximizes consumption per worker, he calls it the golden rule steady state. We'll call it the GR steady state. It is a steady state, but of all the possible steady states in the universe, this is the one that maximizes consumption per worker. Okay, that's the golden rule, Solow says. So the idea behind this steady state is to choose the savings rate that will take you into the maximum consumption per worker. That savings rate will be called the golden rule savings rate. So that's small s, golden rule. There's a unique savings rate that will take you into this special steady state. Well, we know the consumption function starts out as, I shouldn't have put this as a full line. I should have just started it with this. We know the consumption function in terms of workers, the consumption per worker is 1 minus s times small y. That's this first part here, of course. And then we can build in the small y. We know small y is equal to k to the alpha. That's in here. And then it turns out a solution for k in the steady state is s over delta plus n all to the alpha over 1 minus alpha power. It turns out, right? You could look that up, but I happen to know that. I wouldn't try to remember that. Okay, I would try to remember how to solve a steady state. K dot is equal to 0. Savings is equal to break-even investment. That's how I always do these. But we know that this is. I'll tell you that this is true. So I can put that in for K. And I have a maximization problem. I'm trying to maximize this C. So I would changes savings. But notice the savings rate is in two places. It's in here. That's in here. If savings increases, right, then this term rises, and because of the negative sign in front, consumption would fall, right? And the idea is that if people save a greater percentage of their income, consumption, other things being equal, will have to fall. But on the second term is here. And that second term says as savings inside increases, there'll be more capital per worker. Remember, the savings function will shift up, from here to here, S1, S2, and give a break-even line, right? We'll move from 1 to 2, and output per worker will rise, and consumption per worker will rise. This term will rise. So we have two effects. Okay, an increase in the savings rate will have a negative effect here and a positive effect here. Okay, and the question is, right, which one wins, and at what point do we have a maximum consumption? Well, that's a simple maximization. It seems like it's a simple maximization problem. We're maximizing this consumption function with respect to S. That's not so easy, okay? And I'll expand it. Okay, we have to maximize this function. Right? But sometimes it's useful to be clever as opposed to being working something with brute force. Right? If we're clever about this maximization problem, we can do something clever here. We know that the golden rule is a special steady state. And we know something about all steady states. In all steady states, K dot is equal to 0. In all steady states, savings is equal to break-even investment. That's the definition of a steady state. K dot is equal to 0. And that allows us to put this last expression in to the maximization problem. And that makes the maximization problem much easier. So we'll replace S times F of K with delta plus N times K. And when we do that, we're now maximizing this function, and we're maximizing consumption over the variable K. And notice K is in here, and K is in here, and nowhere else. That's an easy maximization problem. If I do this maximization, and you should recall what maximization means, the derivative is typically set equal to 0, and then we check the second order conditions. We'll presume the second order conditions hold, and they do. Maximizing consumption by choosing K means the derivative of the consumption function with respect to K is set equal to 0, and the second order conditions hold. So if I take the derivative of this thing with respect to K, the first term will give me F prime of K, and the second term differentiated with respect to K is just delta plus N. And I have to set them equal to 0, this derivative equal to 0, I'll set it equal to 0. That's simple, okay? And I get an answer, right? The answer is F prime of K is equal to delta plus N. Well, delta plus N are the givens, given that, and F prime of K is just the derivative of the F function. And that F function is K to the alpha, small k to the alpha. Now, that's an easy thing to differentiate and find. A way of interpreting this is we know any F of K, F prime of K, is a slope of the function. It's the slope of the F function. So here's K, here's Y, and here's that F function. That's our favorite shape. This is Y is equal to F of K, and the slope is F prime of K. We learned that in the calculus. And delta plus N is the slope of the break-even line. That's over here. So it says the two slopes are equal. The break-even line slope, and that's supposed to be equal, and the break-even line slope and the slope of the output function, output per worker function, are equal at the golden rule. And since they're supposed to be equal, that would be the golden rule steady state. Okay? The two slopes are equal, and so we can use that to find the golden rule graphically. I'll do that on the next slide. Okay? There's a unique savings rate that will take us in there. So I don't want to do this first. I want to do the, let me see if I have, I'll come back to this slide. Here's it graphically. So here's the slope of the break-even line. I'll come back to that previous line, and we need to put this in, right? We must have F prime of K equal delta plus N. Here's the slope of delta plus N. Here's the slope of the break-even line. That's the idea. Okay. And this would be the golden rule capital stock per worker. So here we go. Here's the slope of the break-even line. Here's F prime of K. That's where they're equal. Here's the golden rule capital stock per worker. This will have to be CGR. That will have to be the maximum consumption that can be fit underneath that curve. And if you eyeball it, it will be. You can see way out here, consumption is the gap here. That's small. Consumption will be the gap here. That's small. This is the biggest consumption that can be fit under that curve. Okay. So that's one way of finding the golden rule, the maximum consumption. There is another way that was on the previous slide. I'm going to backtrack and go back to that and show you another way of calculating this. Both ways are sometimes useful. And it's this one. There's a second condition. I have these slides out of order. There's a second condition to generate the golden rule, and that is a very special and unique savings rate. A savings rate that will take you right into the golden rule. Only one on the whole map, on the whole graph. All right, and we're going to calculate it. Right. First, we know that the golden rule needs the slope of the output function is equal to the slope of the break-even line, where the output per worker function is equal to small k to the alpha. Well, the derivative of that, small k to the alpha, is very easy to calculate. It's alpha times k to the alpha minus 1, and that's this side here, and that has to equal the slope of the break-even line, delta plus n. The next step, I'm going to multiply through both sides by small k, and I get this expression. If I multiply, all right, both sides by small k, I get delta plus n times small k on the right, and on the left, when I multiply by small k, that minus 1 in the exponent disappears, and I have k alpha times k to the alpha equals this, which is the regular old break-even line. Right? This must hold at the golden rule. Next, I know the golden rule is a steady state. It's a special steady state where consumption per worker is maximized. And I know in every steady state, k dot is equal to 0, which means I also know that savings is equal to break-even investment at all steady states. This is the golden rule, steady state. If we compare these two conditions, every steady state must have this one. The golden rule steady state must have this one. If we compare them term by term, what must be the case? It must be the case that this savings rate is equal to alpha. Okay, since this must hold in the golden rule, and this must hold in the steady state, and the golden rule is a steady state, it must be the case that savings is equal to alpha in the golden rule steady state. And that's the condition. I like to write this, the way I write small s is like this, right? And alpha is on the other side. See how they're kind of like two fish? I don't know if you see the two fish are looking at one another. Try to remember it somehow, right? The two fish look at one another. When that's true, when savings is equal to the capital share, and the capital share is a given. And in the United States, recall the capital share is 30%. If the savings rate is equal to the capital share, then you know that the economy is at the golden rule steady state. Unfortunately, in the United States, we know the savings rate, I mentioned this earlier, the US savings rate is 20%. So it's not the case in the US that savings is equal to, the savings rate is equal to the capital share, and that means we're not at the golden rule. Okay, we're not maximizing consumption per worker. But in any case, the conclusion is we have two steady state, two conditions for the golden rule. The first one is that f prime of k is equal to delta plus n. Okay. And the second is that the savings rate is equal to the capital shear, or the two fish are looking at one another. Sometimes you need to use one of these conditions. Sometimes you need to use both of the second condition. Sometimes you need to use both of these conditions. Okay, be careful about that. All right. So I've already done this graphically. I'll show you this. The idea then is the following. Here, I've used the first condition that the slopes are equal. Here's the slope of the output function. Here's the slope of the break-even line. Okay. This is where the slope is equal at this KGR. Then it must be the case that there's a special savings function that goes right in there. That's SGR times K to the alpha, or alpha times K to the alpha, because recall the two fish look at one another when you're at the golden rule. So there we are. That is a special steady state. It's the golden rule steady state. And then this consumption here, that's the golden rule consumption per worker. That's the biggest possible consumption that can be fit underneath this graph. Okay. And the logic of it is that policymakers should try, if they care about the citizens of their country, they should try to make the citizens of their country as happy as possible, to give them as much consumption, not income, but as consumption, as high a consumption per worker as possible. And they should try to get to the golden rule. And the way they can get to that golden rule is by changing this savings rate. If the savings is too high, reduce the savings rate. If the savings is too low, increase the savings rate. So that if you're over here, if you have this kind of savings rate times K to the alpha, you should raise the savings rate. If, on the other hand, you're up here, savings 2 times K to the alpha, you should reduce the savings rate. And in both of those cases, you'll be moving towards the maximum consumption. Okay. In other words, consumption has a hill. Think of it this way. Here's consumption per worker, and here's the savings rate. Consumption per worker has a hill. It's a hill. And this maximum consumption per worker occurs when the savings rate is equal to alpha. The two fish are looking at one another. And if your savings rate is over here at S1, you should increase the savings rate. If your savings rate is out here at S2, you should decrease your saving rate. And in both cases, you'll be going towards the maximum consumption. Right? So let's take a look at that and how this operates, because incredibly, there's a good deal of politics behind all this. Right? Because we've just introduced the idea that policymakers, if they care about, this is a phrase I just made, if policymakers care about the well-being of their citizens in the very long run, over 30, 50, 100 years, then what they should do is alter the savings rate, or take policies that will alter the savings rate to move them closer to the golden rule savings rate. And there's politics involved in doing exactly that. Let's take a look at that. So I want to move to this. The golden rule steady state in the Solow model without technological progress. Suppose we start with a capital stock per worker. We're at some steady state. Small k star is above the golden rule steady state. That means we're going to come at the golden rule from above and come down to it. Okay. And that must mean the savings rate at the moment is too high. I've mentioned a country already with a very high savings rate, China. Savings rate in China is in the neighborhood of 50 to 55%. All right, that's a tremendously high savings rate, probably too high a savings rate to support maximum consumption. The capital share in China is probably around 40% or so, 35 to 40%. Well, that's too high. So I'm talking about China in this example. All right. So if we're looking at a chart like this, and here is a standard steady state. Notice break-even investment here, savings here. That's the intersection. This is where we are. We're at K1, and that's a regular old ordinary vanilla steady state. And you can see consumption per worker. Here's output per worker at 0.1, and consumption per worker is here. That's C1. But that's not the golden rule. If we use the trick of looking at the slope of the break-even line and the slope of the output function, that point has to be the golden rule. Okay, that would be, look at the consumption there, that would be a huge amount of consumption, much higher than the consumption you're already at. Right? That's the logic, and this would be f prime of k, and the slope of the break-even line is delta plus n. This f prime of k function has the same slope as the break-even line, and so that point would be the golden rule. And there's a special savings rate that goes through that point, and it's alpha. And so in this country, they should reduce their saving rate. And when they reduce their saving rate, okay, they will grow, or shrink, I should say, back here. And output per worker along the output per worker function will move along here. So output per worker will actually fall. Right? Investment and savings will jump down, right? They'll jump right down and then fall a little bit more. Okay. But what happens to consumption? Well, consumption started out at C1. Consumption started this big. And then since savings fell, consumption went from here to here. Consumption jumped up. It went from here to here. That's the first amount of consumption, C1 star. And then it jumps down to here, up to here. That's a huge amount of consumption. And then it falls a little bit as both output falls and savings falls. And so we can map out the trajectory of all these variables on the next slide. Right, this is approaching the steady state from above, where the savings rate falls. We'll first take y. Y, and the logic of this graph is the following. This is small y, so this is y over L. This is small c, so this is capital C over L. And this is investment, which is also saving, S over L. Take y first. Going back to the previous slide, right? And the logic of this is at time t0, the savings rate is cut. So the economy is buzzing along time 0 out to t0, and then the savings rate, let me make that a little bit better, and then the savings rate is cut. And what happens back here, the savings rate is cut, and this function shifts down. And then the economy moves, of course, to this lower level of capital stock per worker called the golden rule. So looking at this, what happens to output? Output doesn't, nothing happens initially, and then it falls, and of course it falls along that shape, but the shape is going backwards. It's going in this direction. And so it goes backwards in that direction. That's the shape. Upside down, going backwards. Next, what happens to investment, which is also savings? We'll come back to consumption. Well, going back to the previous line, notice that savings falls, and hence investment falls, and then it falls again along this line as we move to the new golden rule steady state. It jumps down and then falls a little bit more. Look at investment and savings. It jumps down and falls a little bit more. and then levels out. Okay. Finally, consumption. Consumption starts this big, and since the savings rate is falling, consumption is actually rising and then falls a bit. So consumption spikes up and then falls a bit as we get to the new steady state. And that's in fact what's happening here. Consumption, and I think not in yellow, but consumption spikes up and then falls a bit. Falls a bit, but it is always above where it would have been. It's always larger. C golden rule always exceeds the original C. And there's a reason for that. We're going to the golden rule steady state. It doesn't get asymptotic. It's always higher than this black dotted line. Always. Okay. Let's see. So savings and output per worker should fall to maximum. That's right. Because savings falls by more. So if you look at Arya's comment in the chat, savings and output per worker both fall, okay? But notice that savings and investment fall by a lot. Look how big this jump down is, all right? It jumps down and then falls again, whereas output falls a little bit. So look at the consumption function, right? C is equal to 1 minus S times Y, okay? This term is falling, but this term is falling too. But of course, savings is falling by more, so consumption is rising. Do you see that? And the second feature is consumption is spiking up. Consumption spikes up first, it jumps up, going back, because this thing jumps down. It was here to here, and now it's from here to here. So consumption spikes up first and then falls, but it falls to a level that will always be above its former level. This black dotted line is the former level, because we know we're going to the golden rule, which has the maximum consumption in the steady state. Okay. Now, I said there's politics in here, and there is. I've just done the mathematics. I've just done the graph. This slide, which is directly from the textbook, so you can take a look at this in chapter 8, is known as the trajectory of consumption, output, and of course, investment and savings. These are the trajectories of these variables. But I want to talk now about the politics here. Okay, there's really some interesting politics going on here. The politics were first worked out by Robert Solow in 1956. He recognized this, and they were added to by Larry Summers. Larry Summers is a well-known macroeconomist. He was a professor of macroeconomics at Harvard. He was one of Robert Solow's students at MIT. He was the Treasury Secretary under President Bill Clinton. He was the key macroeconomic advisor to the Obama White House during the Obama years. And he was then president of Harvard University. And now he's still a professor at Harvard and a very important macroeconomist. He collaborated with Robert Solow on discussing some of the political ramifications of this model in this particular instance. And Solow and Summers claim that no democracy will ever live beyond the golden rule steady state. That's their claim. Right? That if we go back to the previous slide, right, no democracy, I'll put this in red here, no democracy will ever be, ever, I can spell it, at K1 star, which is greater than the golden rule K1, the golden rule. They'll never be out here. Now I want to explain what they mean by that. Okay? And that comes from the trajectory. Because Solow and Summers say, what is a democracy? A democracy is political competition. And in a democracy, parties and politicians compete with one another. And when they compete with one another, they, to some extent, try to find policies that will make more of the citizenry better off, okay? Because then those citizens will vote for them, they'll get more votes, and they'll be elected to power. So a democracy is a political competition, and politicians can be seen as political entrepreneurs, always searching for the best kinds of policies. Okay? And if we look here at this particular graph, this is the graph of the trajectory of consumption per worker, output per worker, and investment per worker in the steady state as we move from the steady state above the golden rule to the golden rule. A political entrepreneur looking at this, okay, would reason in the following way. Look at what's happening to consumption. If we do this, and the thing we're talking about is this, if we enact policies that will reduce the country's savings rate, okay, then consumption per worker will spike up, right, and always stay above its former level. And so citizens will be better off. Not just any citizens, all citizens, everybody. The current generation, which lives in here, they will be better off because the savings rate will be lower, so their consumption will be higher. And they'll be better off, and they're likely to vote for me and this policy that I'm promoting. Likewise, way out at the tail end, by the time 30, 50, 100 years, by the time the economy achieves its steady state, and going back to the previous slide, here, which is now the golden rule, consumption is still this big. It's very big, much bigger than it started at C1 star, way back here. And so those generations are out here, they're better off. And a politician in a democracy is a political entrepreneur. They can get in front of the public, and now I'm going to pretend I'm a politician, and here's my microphone, and I'll say, the policy I'm installing will make you better off. That's you here, current generation, and make your children and grandchildren better off. That's here. And maybe for the first time in history, the politician would be correct. If the economy starts at a steady state beyond the golden rule steady state and reduces the savings rate so that this happens on this graph, you move from the steady state at K1 star to the golden rule steady state here, then you've made everybody better off. You've made the current generation better off, and you've made their kids and their grandkids and their great-grandkids and all their progeny for all time better off because their consumption will also be higher, way out here. And their insight continues. Of course, it's the current generation that's voters, right? They're the voters. This generation hasn't been born yet. They're way out there, okay? And so the current generation, seeing through this policy, a politician, a political entrepreneur promoting this policy would vote for this politician. And then, of course, the politician would follow through with this policy. Nobody's against it. Nobody. The current generation and future generation, the current generation, if they care about their kids, they want this policy too. And the policy will be installed, and then the economy will go to the golden rule, back to here. So no democracy will ever live at K1 star out here, because political entrepreneurs will rise up, will recognize the opportunity. That's what we're saying. Will recognize the political opportunity and will promote that and come into office and enact it. Furthermore, if no democracies ever live at K1 star for the previous reason, for political competition, then the only countries that do live out at K1 star are not democracies. Okay? They're dictatorships of some kind or another, where the political leadership does not care about its citizenry, does not care ultimately about the welfare of its citizens. Okay? And Solow and Summers argue that the former Soviet Union was an instance of a country, okay, that did live beyond the Golden Rule steady state, did live at a point like K1 star on this graph. Okay? It was, of course, a political dictatorship, a dictatorship of the Communist Party. Back when the Soviet Union existed, okay, it was in political competition with the United States. Right? The politicians didn't compete with one another, with all Communist Party. They competed with the United States. And it was important back then. I know almost nobody in the class remembers this. The Soviet Union fell apart in the early 1990s, 1991, Christmas Day, 1991. But in any case, they were in political competition with the United States, and they competed in many different ways, culturally, in sports. The Olympics were a big competition between the United States and the West, the free countries in the world, and the communist countries behind the Eastern Bloc, behind the Berlin Wall. That was a competition. There was military competition. Client states of both major superpowers fought wars against one another. Two countries never went to war themselves. They had a Cold War. But some of the competition was kind of propagandistic. So the Soviet Union claimed that it had the world's largest steel mills and the world's largest, that generated the most hydroelectric power. It had the largest military bases and the biggest and strongest missiles. And of course, the Sputnik and the space race, they got to space first. They put a satellite into space first. They put a human being into space first, and so on. There was that kind of competition. They made much of the fact that they had the largest factories, the largest production, the largest concrete production, the largest steel production, the largest rubber production. These industries, the military, these kinds of industries are very capital intensive. Huge factories, whole cities as factories. Okay? In other words, a huge capital stock per worker. Right? And of course, if you maintain a huge capital stock per worker, okay, given any depreciation in population growth, okay, then you have to do a lot of savings to support that huge capital stock. Because if the capital stock is very large, even a small percentage of it falling apart every year means you have to do a lot of saving to replace that falling apart capital stock. Even if population growth isn't very fast, because the capital stock is so large, the way we would say that today is the Soviet Union promoted heavy industry, and heavy industry is capital intensive, a huge capital stock per worker. Then as more workers are born, you have to do a lot of savings to give them the same capital stock. And if you have to do a large amount of savings, then you have to compress consumption. Consumption in such a case, at K1 star with a huge capital stock, consumption has to be smaller than it otherwise could be. And of course, the Soviet Union was not in any way a consumer paradise. Consumption was severely compressed. Most of you have probably heard of bread lines, food lines, and so on. Waiting 10 years to get an apartment in Moscow, waiting 15 years to get in a line to get a car. Okay, it was not a consumer paradise. It was a dramatic compression of consumption, so that savings could be big to support a huge capital stock. And of course, it was a dictatorship of the Communist Party. Okay, and so that's Summers and Solow's reasoning that no democracy will ever live beyond the Golden Rule, and only political dictatorships live beyond the Golden Rule because they don't care about the welfare of their citizens. And since the Soviet Union has broken up, the country's gotten smaller. The economy has gotten smaller. It's gone in this direction. The capital stock per worker in Russia no longer depends upon heavy industry, okay, to a great extent. It depends upon extractive industries, right? And output per worker has fallen also, but consumption per worker is much higher than in the Soviet days. They moved exactly, right, or down towards the golden rule steady state. Consumption has increased, even though output per worker, savings per worker, and investment per worker has fallen. Okay. So that's starting from above the golden rule. So now think of the logic. What if you start below the golden rule? Right? Democracies have to live there. Okay. They live below the golden rule or at the golden rule. Solow and Summers say you only happen to live at the golden rule purely by luck. So most democracies live short of the golden rule with a savings rate that's too low to maximize consumption per worker in the steady state. And that's what we turn our attention to next. Here's where you're at a steady state. You're at some kind of K-star, which is a steady state, but it's smaller than the golden rule steady state. So if it's smaller than the golden rule steady state, you want to increase your savings rate up to the savings rate that will take you into the golden rule. And so what that looks like is here. Here's the economy. Here's the plain old ordinary steady state, K1 star. But the golden rule is where f prime of k, recall, is equal to the slope of the break-even line. Here's the f prime of k. Here's the slope of the break-even line. That's here. And so KGR is the golden rule. And you can see the vast amount of consumption that's possible there. This would be consumption at the golden rule. And it's a little bit larger than current consumption in this setup. So what you would want to do is you'd want to generate a higher savings rate, the golden rule savings rate, shift this function up times k to the alpha. And we know what the savings rate is. It's alpha times k to the alpha. And that would take you into the golden rule, which would have the highest consumption per worker. But there's a problem with this. Okay? I want to show you the political problem. This is how it goes. You go from here, shift up the savings function, and the economy goes from this point to the golden rule right here. And you move out there. But look, here's the trajectories. Let's just check the trajectories here. Here's output. Remember, at this point, the savings rate will be increased. Nothing, 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 and then output per worker grows. Go back to the graph, and you can see we go from here to here. So output per worker does grow along this. And investment would jump up. Remember, investment is savings per worker. It would jump up and then grow a little bit more. Jump up and then grow a little bit more. Let's go back. Savings jumps up and then grows a little bit more. But what happens to consumption? Okay. Consumption spikes down and then grows, and it grows to a point that has to be higher than the formal level because it's going to the golden rule where consumption is maximized. And recall, consumption is 1 minus S times Y. And S has to rise, but Y is constant for a moment. And if S rises and Y is constant, at least initially, consumption per worker falls. It jumps down. And sure enough, that's here. And then it eventually rises as Y rises. Y will now, right? Y will now increase and consumption will increase. And sure enough, it does increase. And the political problem here, I'm just going to take 30 more seconds more. The political problem, do you see where the political problem is? The political problem is right in here. That's the current generation. The current generation of workers. Their consumption per worker will fall for a while. And their kids and grandkids will be better off, but they will have suffered a consumption loss And recall, they're the ones who are alive at the moment. They're the voters. And so a political entrepreneur in a democracy who proposes a policy to raise the savings rate in this situation, when the steady state is less than the golden rule, that political entrepreneur faces voters, the current generation, who will be worse off. This may take 20 years. Who will be worse off for 20 years. And a politician would be having saying the following: I'm going to do something that will benefit your kids, but it's going to make the economy, you worse off for the next 5, 10, 15, 20 years. That is not politically attractive. And if it's not politically attractive, current voters may not vote for it. And if they do not vote for it, the economy cannot achieve the golden rule. A democracy cannot achieve a golden rule from below. It stays where it is and can't get out here. And that means democracies fail, because of the politics of the golden rule from below, fail to do as best they can for their citizens, cannot maximize their consumption per worker. And what I've done here is I've completed chapter 8. We have finished the Solow model with depreciation and population growth, and talked about the golden rule. Part of this is in chapter 9. The introduction of population growth is part of chapter 9. We'll draw a line under where we are right here on this graph, and return to meet with one another next Tuesday. This weekend's Canvas quiz will cover up to exactly this point and no further. All right, so that's just to the end of chapter 8 and the discussion of the Solow model with population growth in chapter 9. Okay. Good luck. We'll see you next Tuesday. I'll be sending